Of all the spectacles the universe has to offer, few are more majestic than a spiral galaxy. It's a silent, spinning city of 100 billion stars, each one held in a stately, cosmic dance by the force of gravity. It is a vision of perfect celestial mechanics, a balance of motion and mass playing out on a scale that just humbles the imagination. The stars, the dust, the luminous clouds of gas, they all orbit a common center, bound together by their mutual gravitational pull, creating the glorious structures we see through our telescopes. It's a picture of stability, of permanence. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But this beautiful dance is hiding a violent secret. For decades, we've known that these galaxies are spinning so fast they should be tearing themselves apart, flinging countless stars into the cold, empty void. The gravity from all the matter we can see, every star, every planet, every grain of dust, is nowhere near strong enough to hold on. And yet, they aren't flying apart. The Milky Way is intact. Andromeda is intact. The countless galaxies that populate the cosmos remain bound together in their elegant spiral forms. This isn't a small error. It's a universe-sized discrepancy. It points to a profound truth, that the universe we see is only a tiny fraction of what's actually there. We discovered that the universe is held together by an invisible skeleton, a substance we cannot see, cannot touch, and can barely comprehend, but that makes up most of reality. So, if it's not the stars and gas, what is actually holding the universe together? The answer will take us on a journey from the edge of a spinning galaxy to the very beginning of time, revealing a hidden cosmos that dictates the fate of everything. The rules of the road. Gravity as we know it. To understand the crisis that shook cosmology to its core, we first have to appreciate the rules. The story of gravity, as we first understood it, is a story of beautiful simplicity. It begins, as legend has it, with an apple. When Isaac Newton saw an apple fall from a tree, he had a breathtaking insight. The same force that pulled the apple to the ground was also holding the moon in orbit around the Earth. It was a universal law. Gravity wasn't just some local thing, it was the engine of the heavens. Newton's law of universal gravitation is beautifully elegant. It says the force of gravity between two objects depends on just two things: how much stuff they're made of, their mass, and how far apart they are. The more massive the objects, the stronger the pull. The farther apart they are, the weaker the pull. Specifically, the force drops off with the square of the distance. If you move twice as far away, the gravitational force becomes 4 times weaker. 3 times as far, and it's 9 times weaker. This inverse square law is the fundamental rule of the road for the cosmos. And for centuries, it worked perfectly. It explained a falling apple, the moon's orbit, and the grand celestial waltz of our solar system. Think about our own cosmic neighborhood. The Sun, containing over 99.8% of all the mass in the solar system, sits at the gravitational center. Its immense gravity calls the shots. Mercury, the innermost planet, feels the Sun's pull most intensely. To keep from falling in, it has to race around the Sun at a blistering 47 kilometers per second. Earth, farther out, feels a weaker pull and travels at a more leisurely 30 kilometers per second. And way out in the cold, distant frontiers, Neptune just ambles along at 5 kilometers per second. This is exactly what Newton's law predicts. The farther you are from the central mass, the slower your orbital speed. This predictable, graceful slowing of objects with distance is known as a Keplerian decline, named after Johannes Kepler, who first described how planets move. For astronomers, this wasn't just a description of our solar system, it was a blueprint for how any gravitationally bound, rotating system should behave. And for a long time, we assumed galaxies were no different. A spiral galaxy, with its bright, dense core, looks a lot like a scaled-up solar system. Most of the stars, and therefore most of the visible mass, are packed into that central bulge. So, the expectation was clear: stars near the center should be moving fast, while stars on the outer fringes should be moving much, much more slowly. Just like Mercury and Neptune. If you were to plot these expected speeds on a graph, speed on one axis, distance from the center on the other, you'd expect to see the line rise quickly near the middle and then fall off dramatically toward the edge. This graph, this rotation curve, was the gold standard prediction. It was the logical next step from the laws of gravity that had governed our understanding of the universe for 300 years. No one had any serious reason to doubt it. When astronomers finally developed the tech to measure these galactic speeds with precision, they expected to simply confirm what they already knew. They were expecting to prove Newton right, once again. Instead, they stumbled upon a crisis that would redefine reality itself. They found that the rules of the road, the very laws that governed our own world, were being broken on a galactic scale. The universe was not behaving as it should. The cosmic crisis. A devastating observation. The first hint that something was profoundly wrong came not from some grand, sweeping survey, but from a single, cantankerous astronomer studying a dense cluster of galaxies. In 1933, the Swiss-American astrophysicist Fritz Zwicky turned his attention to the Coma Cluster, a sprawling metropolis of thousands of galaxies some 320 million light-years away. Zwicky was a brilliant, abrasive, and often overlooked figure, known for his creative insights and, well, his difficult personality. He decided to measure the speeds of the galaxies at the edge of the cluster as they orbited the cluster's center. Using the physics of the virial theorem, he made a startling calculation. The galaxies were moving at tremendous velocities, far too fast for the cluster to hold onto them. Based on the light from all the visible galaxies, he calculated the total mass and, therefore, the total gravitational pull. The numbers didn't add up. The cluster simply did not have enough visible mass to keep those speeding galaxies from flying off into space. To account for this, Zwicky proposed that the cluster must contain some kind of invisible matter, which he called dunkle materie, or dark matter. He calculated that there had to be many times more of this dark matter than visible matter to hold the Coma Cluster together. It was a radical idea, and for the most part, the scientific community ignored it. Zwicky's calculations had their uncertainties, and he was a known eccentric. His revolutionary idea was dismissed as a curious anomaly, a footnote in the history of astronomy, for nearly 40 years. The mystery, however, didn't go away. It just waited for the right person with the right tools. That person was Vera Rubin. In the 1960s and 70s, Rubin was an astronomer at the Carnegie Institution in Washington, D.C. At a time when the field was heavily dominated by men, she was a persistent and meticulous scientist. She decided to tackle a problem many considered uninteresting: the precise rotation of galaxies. She teamed up with instrument maker Kent Ford, who had developed a new, highly sensitive spectrograph. This device was a game-changer. It splits light from an object into its spectrum of colors. Within that spectrum, you can see the chemical makeup of the object, but more importantly, you see its motion. If an object is moving towards us, its light is compressed, shifting spectral lines toward the blue end of the spectrum, a blue shift. If it's moving away, its light is stretched, shifting lines toward the red, a red shift. By measuring these shifts across a galaxy, Rubin and Ford could create a detailed map of its rotation with stunning accuracy. Their first target was the Andromeda Galaxy, our closest spiral neighbor. Just like everyone before them, they expected to find a Keplerian decline. They expected to see stars at the edge of Andromeda moving slowly. What they found was shocking. As they measured farther and farther out from the bright center, the rotation speed didn't drop. It just stayed flat. Stars on the distant, dim periphery of the galaxy were moving just as fast as stars much closer to the center. This was a flagrant violation of Newton's laws. It was like finding that every planet in our solar system, from Mercury to Neptune, orbited the Sun at the exact same speed. It was physically impossible. At first, Rubin thought it might be an error, or something unique to Andromeda. So she and her team expanded their survey. They observed dozens of other spiral galaxies. And everywhere they looked, they found the same thing. Galaxy after galaxy, the rotation curve was flat. The outer stars were all moving too fast. The implication was staggering. For these stars to be moving so fast without being flung out, there had to be an immense amount of gravitational pull holding them in. And that gravity couldn't be coming from the visible matter. When Rubin calculated the mass required, she found that galaxies needed at least 5 to 10 times more mass than could be accounted for by all the stars and gas they could see. Her work, published throughout the 1970s, was undeniable. Unlike Zwicky's observations, which could be dismissed as a quirk of galaxy clusters, Rubin's data was systematic, precise, and consistent. The problem wasn't an anomaly, it was a fundamental feature of the cosmos. Galaxies were not what they seemed. By all rights, these beautiful cities of stars should be ruins. The cosmic crisis was no longer a fringe idea. It was now the central, unavoidable mystery in astrophysics. The search for Zwicky's Dunkel Materie was on. The ghost in the machine. The hunt for the missing mass. The flat rotation curves presented a stark choice. Either our understanding of gravity was wrong, or galaxies were filled with a vast amount of invisible mass. While some physicists explored modifying Newton's laws, most followed the evidence where it led, to the ghost in the machine. Something was there, but we couldn't see it. This something couldn't just be ordinary matter that was dark. Not vast clouds of dust, which we'd see in infrared. Not swarms of dead stars or rogue planets. There wouldn't be nearly enough of them, and they'd occasionally block starlight. And while a tiny fraction might be black holes, it couldn't be a whole sea of them. No, the vast majority of this had to be something entirely new. Something that doesn't interact with light or any other form of electromagnetic radiation. It wasn't just dark, it was fundamentally invisible. This is the modern definition of dark matter. Its primary known property is that it has mass, and therefore gravity. It doesn't emit, absorb, or reflect light. It's also thought to be cold, meaning it was moving slowly in the early universe, and it's largely collisionless. For the most part, it passes through ordinary matter through stars, planets, and our own bodies almost as if it were a ghost. The chance of an interaction is incredibly small, but not zero. With this concept, a solution to Vera Rubin's paradox began to take shape. The reason outer stars are moving so fast is that the visible galaxy, the spiral of stars and gas, is just the tip of the iceberg. Astronomers proposed that every galaxy is embedded within a massive, spherical, halo of dark matter. This halo is enormous, extending far beyond the visible edges of the galaxy. While the visible disk of a galaxy like the Milky Way might be 100,000 light-years across, its dark matter halo could be up to 2 million light-years in diameter. This model elegantly explains the flat rotation curves. Near the center of a galaxy, a star feels the gravity of the mass inside its orbit. As it moves farther out, it should feel less gravity as it leaves more visible mass behind it. But in a galaxy with a dark matter halo, as a star moves farther from the center, it's also moving deeper into this vast sphere of invisible mass. More and more of the halo's mass is now inside its orbit. The effect is a cosmic balancing act. As the gravitational pull from the visible matter decreases, the pull from the encompassing dark matter increases. These two effects work to create a nearly constant gravitational force across the galaxy, which leads to the flat rotation speed of the outer stars. The impossible speeds Vera Rubin observed were the smoking gun signature of these colossal, invisible halos. The numbers are astonishing. To make the math work, dark matter has to be the dominant ingredient of the universe's matter. The current consensus is that all ordinary, visible matter, every star, planet, and person, makes up only about 5% of the total mass and energy of the universe. Dark matter makes up about 27%. It outweighs all of us by more than 5 to 1. The remaining 68% is thought to be an even more mysterious substance called dark energy, which is the leading explanation for the accelerating expansion of the universe. Think about that for a moment. We live in a universe where 95% of reality is hidden from us. The stuff that makes our world is just a sprinkle of cosmic dust on a vast, unseen structure. This wasn't just solving a puzzle about galaxy rotation, it was a fundamental re-evaluation of our place in the cosmos. We didn't just discover a new particle, we were discovering a new reality, one governed by a substance we can only infer through its gravitational whisper. The ghost in the machine turned out to be the machine itself. The invisible skeleton. Building a universe. The discovery of dark matter halos solved the problem of spinning galaxies, but its implications were far grander. This invisible substance wasn't just a patch to fix a local problem, it was the master architect of the entire cosmos. Evidence for its role as the universe's hidden skeleton came from two other, completely independent lines of inquiry: the bending of light and the afterglow of the Big Bang. First, let's talk about bending light. Einstein's theory of general relativity tells us that massive objects warp the fabric of spacetime. Because light travels through spacetime, its path gets bent when it passes a massive object. This is called gravitational lensing. Imagine light from a very distant galaxy traveling towards us. If it passes a massive galaxy cluster along the way, the cluster's immense gravity acts like a lens, bending and distorting the light. When we look through our telescopes, we don't see the distant galaxy as it is, but as a warped, stretched out arc, or even multiple smeared images. Here's the crucial part. The amount of distortion is a direct measure of the asterisk total mass of the cluster. It doesn't care if the mass is visible or invisible, gravity bends light all the same. And when astronomers measured the mass of galaxy clusters using gravitational lensing, they found the exact same discrepancy that Zwicky and Rubin had. The visible galaxies made up only a small fraction of the mass needed to produce the intense lensing effects they saw. By mapping the distorted images, astronomers can create a mass map of the cluster, revealing a giant, smooth cloud of matter that perfectly matches the predicted shape of a dark matter halo, with the visible galaxies nestled inside like bright jewels. We are literally seeing the shadow of dark matter, written in bent starlight across billions of light years. The second, and perhaps most compelling, piece of evidence comes from the very dawn of time: the cosmic microwave background, CMB. The CMB is the faint heat left over from the Big Bang, an echo of creation that fills all of space. Emitted when the universe was just 380,000 years old, it's a baby picture of the cosmos. Telescopes have mapped this ancient light in incredible detail, revealing tiny temperature fluctuations, hot and cold spots that represent tiny density differences in the primordial soup. These tiny fluctuations were the seeds from which all cosmic structure, including galaxies, eventually grew. The denser spots were the gravitational wells that would pull in more matter and collapse to form the structures we see today. But there was a huge problem. In the early universe, the cosmos was filled with a hot, dense plasma of particles and intense radiation. This radiation exerted enormous outward pressure, which would have smoothed out any clumps of ordinary matter that tried to form. Like a powerful wind blowing away a sandcastle as you try to build it, the radiation pressure should have erased these clumps before they had a chance to grow into anything. There simply wasn't enough time since the Big Bang for the weak force of gravity to overcome this pressure and form the vast galaxies we see today. The universe should be a smooth, uniform soup of gas. This is where dark matter plays its most crucial role. Because dark matter doesn't interact with light or radiation, it was completely immune to this pressure. While ordinary matter was being blasted around in the primordial storm, dark matter could calmly begin to clump together, guided only by gravity. It started forming gravitational scaffolding long before normal matter could. Then, once the universe cooled and the radiation pressure subsided, ordinary matter was finally free to fall into the deep gravitational wells that dark matter had already carved out. Galaxies didn't form on their own, they formed on top of a pre-existing, invisible framework. Dark matter gave structure formation a critical head start. Without it, none of us would be here. When cosmologists run computer simulations of the universe's evolution, they can only reproduce the cosmos we see today if they include dark matter. In these simulations, over billions of years, dark matter's gravity pulls it into a vast, interconnected network of filaments and voids, a structure known as the cosmic web. This web is the true skeleton of the universe. The filaments are colossal bridges of dark matter stretching across millions of light years, and at their intersections sit the great clusters of galaxies. The galaxies themselves are just the luminous froth that has collected along these unseen threads, like dewdrops on a spider's web. The evidence is overwhelming. Dark matter isn't just holding individual galaxies together. It built them. It arranged them. It's the invisible architect of the entire cosmic landscape. The unfinished search. What is it? We know it's there. We can't see it, but we can feel its presence everywhere. We see its effect in the impossibly fast spin of galaxies, the bent light from distant quasars, and the very blueprint of the universe. Dark matter is the invisible skeleton upon which our reality is built. The evidence is so robust that it's a cornerstone of the standard model of cosmology. But this raises the biggest unanswered question in physics: what is it? For decades, the leading candidates have been hypothetical particles known as WIMPs, or weakly interacting massive particles. As the name implies, WIMPs are thought to be heavy particles that interact only through gravity and the weak nuclear force. This weakly interacting nature is key. It explains why they're so hard to detect. To hunt for them, scientists have built detectors deep underground, using huge tanks of ultra-pure liquid xenon. The idea is that, very rarely, a WIMP might collide with a xenon nucleus, producing a tiny flash of light. Despite years of searching with ever-increasing sensitivity, these direct detection experiments have so far found nothing. The silence from these deep underground labs is profound. Another leading candidate is the axion. Axions are incredibly lightweight particles, potentially 1 billion times lighter than an electron, that were first proposed to solve a completely different problem in particle physics. Like WIMPs, they would barely interact with anything and would have been produced in vast quantities in the Big Bang. Experiments searching for axions use powerful magnetic fields, hoping to convert a stray axion into a detectable photon. This search, too, is ongoing. Of course, with no direct detection, some scientists continue to ask if we might be on the wrong track entirely. Could the problem be with gravity itself? This alternative idea is known as MOND, or modified Newtonian dynamics. Proposed in the 1980s, MOND suggests that gravity works as expected where it's strong, like in our solar system, but changes its behavior where it's extremely weak, like in the outer parts of galaxies. In this theory, there is no dark matter. The faster star speeds are just a consequence of gravity being slightly stronger over large distances than we thought. MOND is remarkably successful at explaining galaxy rotation curves, often more simply than dark matter models. However, it struggles to explain the evidence from galaxy clusters and, most critically, the intricate patterns in the cosmic microwave background. To make MOND compatible with these larger-scale observations, it often requires extra fields and parameters, losing some of its original simplicity. While it remains an area of active research, most physicists agree the bulk of evidence points more strongly towards a new particle. The search continues, driven by the profound realization that the answer, whatever it is, will revolutionize physics. Discovering the nature of dark matter wouldn't just be adding another particle to the list, it would be our first real glimpse into the 85% of matter in the universe that has, until now, remained completely hidden from us. We began with a simple, beautiful image, a spinning galaxy. And we found a paradox. A cosmic spectacle that, according to the laws of physics we held dear, shouldn't exist. This journey has taken us from the confounding speeds of stars to the warped fabric of space-time and all the way back to the first light of creation. At every step, we found the same ghostly footprints, the same gravitational signature of a substance we cannot see. What holds the universe together is not the brilliant light of 100 billion stars. It is the silent, immense gravity of an invisible cosmos. The reality we perceive, the one made of atoms, of planets, of people, is just the delicate embroidery on a vast, dark tapestry. Dark matter is the scaffold, the skeleton, the invisible architecture that allowed galaxies to form and that continues to bind them against the void. The fact that we haven't yet identified the particle responsible isn't a failure, it's the signature of a truly profound scientific quest. It's a reminder that we are still in the early days of exploring our universe, mapping a continent whose true scale we are only just beginning to appreciate. The search for dark matter is more than a hunt for a missing particle. It is a search for a fundamental understanding of our reality. It challenges us to look beyond the light and to comprehend the true, and largely invisible, nature of the cosmos. The greatest discoveries, it seems, still lie hidden in the dark. If this journey into the invisible universe has expanded your view of reality, be sure to subscribe and hit the notification bell for more explorations into the cosmos. The universe is full of mysteries, and we're here to unravel them together. And now I want to hear from you. What do you think dark matter could be? A new particle? A flaw in gravity? Let us know your theory in the comments below. The first clue: galaxies that spin too fast. Imagine looking up at the night sky on a quiet evening. Thousands of stars hang above you, scattered across the darkness. Some appear faint, some bright, and if you watch long enough, they seem completely still. The sky feels calm, almost frozen in time. But nothing up there is truly still. Every star in our galaxy is moving, and not slowly. Our own sun, the quiet star that warms Earth every day, is currently racing around the center of the Milky Way at roughly 800,000 kilometers per hour. At that speed, you could travel around the Earth more than 20 times in a single hour. Yet we never feel this motion. The galaxy carries us gently along, like passengers on an enormous cosmic carousel. For a long time, astronomers assumed they understood how this carousel worked. The idea seemed simple. Gravity holds galaxies together. Just as the Earth orbits the Sun because of gravity, stars orbit the center of their galaxy for the same reason. The mass concentrated near the center pulls everything inward, preventing stars from flying away into intergalactic space. It was a neat picture, elegant, predictable, and for decades, no one seriously questioned it. But then astronomers began to measure something carefully. They measured how fast stars move at different distances from the center of a galaxy. And what they found quietly shattered the old understanding of the universe. To understand why, it helps to imagine a familiar system, our solar system. The planets orbit the Sun in a very predictable way. Mercury, the closest planet, moves incredibly fast. It completes an orbit in just 88 days. Earth moves more slowly, taking one full year. Neptune, far out at the edge of the solar system, drifts along much more slowly still, taking 165 years to circle the Sun. The reason is simple. The Sun contains almost all the mass in the solar system. Gravity weakens with distance, so the farther a planet is from the Sun, the weaker the gravitational pull it feels. As a result, distant planets must move more slowly to remain in stable orbit. If they moved too fast, they would simply escape. Astronomers expected galaxies to behave the same way. Near the center of a galaxy, Where most of the stars and gas appear to be concentrated, stars should move very quickly. Farther out, where visible matter becomes sparse, stars should orbit more slowly. The pattern should resemble a downward slope, fast in the center, gradually slowing toward the edges. For a long time, this expectation seemed perfectly reasonable. But when astronomers began measuring the rotation of entire galaxies in the mid-20th century, something strange appeared. The stars at the outer edges were not slowing down. Not at all. They were moving just as fast as the stars closer to the center. Imagine a giant spinning merry-go-round. Normally, the outer horses should move more slowly if the engine powering the ride is located at the center. But in galaxies, the opposite appeared to be happening. The outer regions were spinning far faster than gravity should allow. In fact, many of those stars were moving so quickly that, according to the known laws of gravity, they should have been flung out into deep space long ago. Yet they remained exactly where they were, orbiting calmly, held in place by something invisible. Astronomers double-checked their measurements. Perhaps the telescopes were wrong. Perhaps the calculations were flawed. But the data kept saying the same thing. Galaxy after galaxy showed the same mysterious behavior. The stars were moving too fast, and the gravity produced by visible matter, the stars, gas, and dust we could see, simply wasn't enough to hold them together. Something else had to be there. Something massive. Something invisible. One of the astronomers who helped reveal this mystery was Vera Rubin. In the 1970s, Rubin carefully measured the rotation speeds of stars in the Andromeda Galaxy and many others. She used spectroscopic techniques that allowed astronomers to determine how quickly stars were moving by observing tiny shifts in their light. Her observations were astonishing. Instead of slowing down with distance, the rotation speed of galaxies stayed almost perfectly flat. This pattern is now called a galaxy rotation curve. And it should not exist. If galaxies contained only the matter we can see, their rotation curves would slope downward, like the solar system. But the real curves stayed level, flat, stable, almost as if a vast hidden mass surrounded the galaxy, extending far beyond the visible stars. Rubin herself described the realization with quiet clarity. Galaxies were behaving as though they were embedded inside enormous halos of unseen matter. Not small halos. Gigantic ones. Much larger than the galaxies themselves. These halos had mass. A lot of mass. Enough to keep the outer stars moving at extraordinary speeds without escaping. But there was a problem. No telescope could see this matter. No instrument detected light from it. It did not glow. It did not reflect. It did not absorb radiation in any obvious way. It was simply there, invisible. For a while, some astronomers hoped there might be a simpler explanation. Perhaps galaxies contained huge numbers of faint stars too dim to detect. Maybe clouds of cold gas were hiding in the darkness. Or maybe the laws of gravity behaved differently at enormous scales. But as the data improved, these possibilities began to collapse. There was far too much missing mass. Too much for dim stars. Too much for hidden gas. Too much for any ordinary explanation. The universe seemed to contain vast amounts of matter that did not interact with light at all. Matter that could only be detected through its gravitational pull. It was like discovering the skeleton of an animal by watching the way its skin moved. You cannot see the bones, but the shape they create reveals their presence. And slowly, astronomers realized something extraordinary. The galaxies we see, the glowing spirals and clusters of stars, may only be the visible decoration of something much larger. Beneath them lies a massive invisible framework, a hidden structure, a cosmic skeleton, a structure made of something we now call dark matter. And if that invisible skeleton truly exists, then it means something profound. Most of the universe is not made of stars, not planets, not gas, not anything we can see. Instead, the universe may be built mostly from something completely unknown. something that surrounds galaxies like a vast invisible ocean, something that holds the cosmos together, quietly, relentlessly, and almost completely unseen. If this idea is correct, then the stars we see in the sky are only a small part of reality, a thin glowing layer floating on top of an enormous hidden structure, like lights scattered across the surface of a dark, invisible machine. And the deeper astronomers looked, the clearer it became. The universe is not just stranger than we imagined, it may be stranger than we can imagine, because whatever dark matter is, it is everywhere, and without it, galaxies like ours might never have formed at all. To understand just how strange this discovery was, astronomers began drawing simple graphs. On one side of the graph, they placed distance from the center of a galaxy. On the other side, they placed the speed of the stars orbiting that center. This produced what scientists call a rotation curve. If galaxies behaved like our solar system, the curve should rise near the center, where gravity is strong, and then slowly fall as distance increases. Picture a hill that gradually slopes downward. But that is not what the data showed. Instead of sloping downward, the curves flattened out. After a certain distance from the center, the speed of stars stopped decreasing. It simply stayed almost constant. Stars near the outer edge of a galaxy were moving just as fast as stars much closer to the middle. It was as if the galaxy contained far more mass than anyone could see. And that mass seemed to extend far beyond the glowing spiral arms we observe through telescopes. At first, this result felt almost impossible. Gravity, after all, is not mysterious in the way it behaves. Its strength depends on mass. If you know how much mass something contains, you can calculate how strongly it pulls on nearby objects. Astronomers could estimate the total visible mass of a galaxy fairly easily. They counted the stars, measured the gas clouds, and analyzed the light emitted from billions of distant suns. All of that matter combined still wasn't enough. Not even close. In many galaxies, the stars in the outer regions were moving 2 or 3 times faster than gravity should allow. If those stars were held only by the visible matter inside the galaxy, they should have escaped long ago. The galaxy should have gradually unraveled, like a spinning firework throwing sparks into the darkness. But galaxies were stable. Their stars remained bound together, orbit after orbit, for billions of years. Something unseen was clearly adding extra gravity. Imagine walking into a quiet room and seeing a chandelier hanging from the ceiling. The chain holding it up is invisible. You cannot see it, but you immediately know it must be there. Otherwise, the chandelier would fall. Dark matter reveals itself in much the same way. Astronomers cannot see it directly, but galaxies behave as if enormous amounts of hidden mass are holding everything together. Without it, the entire structure would collapse. As telescopes improved, astronomers began studying galaxies in greater detail. They measured rotation curves not just for a few galaxies, but for dozens, then hundreds. Spiral galaxies, elliptical galaxies, massive galaxies, small ones. And again, the same pattern appeared. Flat rotation curves. No matter where they looked, the outer stars were moving too quickly. The conclusion became increasingly difficult to avoid. Galaxies were surrounded by massive halos of invisible matter. These halos were enormous, often extending 5 to 10 times farther than the visible galaxy itself. Imagine the Milky Way as a glowing disk of stars about 100,000 light-years across. Now imagine an invisible sphere surrounding it, stretching hundreds of thousands of light-years into space. That sphere would contain far more mass than the galaxy's stars and gas combined. This unseen halo is what prevents galaxies from tearing themselves apart. Once scientists began thinking about galaxies this way, the universe started to look very different. Instead of bright islands of stars floating freely through space, galaxies appeared to be embedded inside massive invisible structures, like glowing cities built on top of vast underground foundations. And this raised a profound question. If galaxies sit inside halos of dark matter, how much of the universe is actually made of this mysterious substance? The answer, as it turned out, was astonishing. When astronomers compared the total visible matter in the universe with the amount of gravity required to explain cosmic motion, they found a massive discrepancy. Visible matter, everything we can see with telescopes, makes up only a small fraction of the total. Stars, planets, gas clouds, dust, nebulae, all of it together accounts for only about 5% of the universe. 5%. That means everything familiar to us. Every star that has ever shone, every galaxy ever observed, every atom in your body, belongs to a tiny minority of cosmic matter. The remaining 95% is something else. About 27% appears to be dark matter, and the rest is something even stranger, called dark energy, which seems to drive the expansion of the universe itself. But dark energy is another mystery for another time. For now, the important realization was this: most of the gravitational structure of the universe is controlled by matter we cannot see. The more astronomers examined the cosmos, the clearer this invisible framework became. Galaxies cluster together into groups. Groups gather into enormous clusters. Clusters connect through vast filaments stretching across hundreds of millions of light years. And computer simulations showed that these structures form naturally if dark matter dominates the mass of the universe. Without dark matter, galaxies would not form properly. The early universe would have remained too smooth, too diffuse. Stars might never have gathered into the beautiful spirals and glowing galaxies we see today. In a very real sense, dark matter may have acted as the scaffolding of the cosmos. Long before the first stars ignited, invisible clumps of dark matter began pulling ordinary matter toward them. Gas slowly gathered inside these gravitational wells. Eventually, that gas collapsed into stars, and galaxies were born. If this picture is correct, then every galaxy you see in the night sky is simply the visible tip of a much larger invisible structure, a luminous trace outlining a hidden cosmic skeleton. But this discovery created a new puzzle. If dark matter is everywhere, why can't we see it? Stars shine because nuclear reactions inside them release energy as light. Gas clouds glow when radiation excites their atoms. Even cold dust can be detected by the faint infrared radiation it emits. But dark matter does none of these things. It does not glow. It does not absorb light. It does not reflect radiation. As far as we can tell, it interacts with normal matter only through gravity. That makes it incredibly difficult to study. Astronomers cannot photograph it directly. Instead, they must infer its presence from the way gravity bends the motion of stars, galaxies, and even light itself. And in the next clue that scientists uncovered, gravity would reveal something even stranger. Because dark matter doesn't just affect the motion of stars, it can also bend light from distant galaxies, warping space itself. And when astronomers began observing that effect, they discovered that the invisible skeleton of the universe is even larger than anyone first imagined. As the evidence for dark matter grew stronger, astronomers began to accept a strange but increasingly unavoidable idea. The universe was not built only from the matter we can see. Instead, every galaxy appeared to be sitting inside a vast, invisible cloud of mass. A halo that extended far beyond the glowing stars and gas visible through telescopes. This halo was not just a small addition to the galaxy. It was enormous. In fact, in most galaxies, the dark matter halo contains far more mass than the visible galaxy itself. Imagine looking at the Milky Way from far away. You would see a wide, elegant spiral of stars stretching across space, glowing softly against the darkness. Billions upon billions of suns orbiting the galactic center. But what you would not see is the far larger structure surrounding it, an enormous sphere of dark matter, extending hundreds of thousands of light years outward. The stars form only the bright center of that structure. The real gravitational engine of the galaxy lies in the invisible halo around it, and this halo is what keeps the galaxy stable. Without it, the Milky Way would slowly fall apart. Stars in the outer regions would drift away, escaping into intergalactic space. Over billions of years, the galaxy would gradually dissolve, but the dark halo prevents that from happening. Its gravity quietly binds everything together. Every orbit, every spiral arm, every glowing cluster of stars, held in place by something we cannot see. This realization changed the way astronomers thought about galaxies. Instead of thinking of galaxies as isolated systems of stars, scientists began to see them as visible tracers of a much larger structure. The stars are simply the luminous parts of something deeper, like lights on the surface of a hidden machine. And once astronomers started looking for this hidden structure, they began to find more and more evidence that it was real. The next clue did not come from the motion of stars. It came from something even more subtle: the bending of light itself. To understand this, we have to take a small detour into one of the most beautiful ideas in physics. Gravity does not only pull on matter. According to Einstein's theory of general relativity, gravity also bends space. Massive objects distort the fabric of space and time around them, creating curves that other objects follow. Even light follows those curves. If a beam of light passes near a massive object, its path will bend slightly, pulled by the curvature of space itself. This effect is known as gravitational lensing. It is called a lens because gravity can act like a giant cosmic magnifying glass. When light from a distant galaxy passes near a massive object on its way toward Earth, that light can be bent and distorted. Sometimes the distant galaxy appears stretched into arcs. Sometimes its image appears doubled or multiplied. And in rare cases, it forms a nearly perfect circle of light known as an Einstein ring. These strange distortions allow astronomers to measure how much mass is present in the object doing the lensing, even if that mass is invisible. And when scientists began studying gravitational lensing around galaxy clusters, they found something remarkable. The bending of light revealed far more mass than the visible galaxies could account for. In some clusters, the total mass required to produce the observed lensing effects was 5 or even 10 times larger than the mass of all the stars and gas combined. The missing mass was everywhere, surrounding galaxies, filling clusters, stretching across enormous regions of space. It was as if the entire universe was threaded with an invisible gravitational web. Once again, dark matter offered the simplest explanation. Clusters of galaxies appeared to sit inside massive reservoirs of dark matter. These reservoirs bent light from distant galaxies passing behind them, producing the gravitational lensing effects astronomers observed. And because lensing depends only on gravity, it allowed scientists to map the distribution of dark matter even though they could not see it directly. The maps that emerged were astonishing. Instead of smooth clouds of invisible mass, the universe appeared to be organized into a vast network of filaments and clumps. Dark matter gathered into long strands stretching across millions of light years. At the intersections of these strands, galaxies formed. Clusters of galaxies formed. Entire superclusters formed. The visible universe seemed to follow the shape of this invisible framework. Astronomers began calling this structure the cosmic web, a giant network of matter stretching across the observable universe. Galaxies were not randomly scattered through space. They were arranged along the filaments of this web, like beads on invisible threads. And dark matter appeared to form the underlying skeleton that gave the web its shape. Computer simulations confirmed this picture. When scientists created models of the early universe and allowed dark matter to dominate the gravitational structure, something fascinating happened. The simulations naturally produced the cosmic web. Filaments formed. Clusters formed. Galaxies emerged in exactly the same patterns astronomers were observing through telescopes. But when the simulations removed dark matter and used only ordinary matter, the universe looked completely different. The structures failed to form properly. Galaxies appeared too small, too scattered, too weakly bound. Without dark matter, the universe we see today simply could not exist. It was like trying to build a cathedral out of mist. There was nothing strong enough to hold the structure together. Dark matter provided that structure. It formed the deep gravitational wells that allowed gas to gather. Stars ignited inside those wells. Galaxies slowly grew. Over billions of years, the invisible framework shaped the visible universe. And all of this raises an extraordinary possibility. When you look up at the night sky, the stars you see may be only the faintest surface layer of reality. Beneath them lies something much larger, a hidden architecture, an invisible network of matter stretching across unimaginable distances, a skeleton holding the universe together, quietly shaping the motion of galaxies, bending the path of light, guiding the formation of cosmic structures, all without ever revealing itself directly. Which leads to one of the deepest mysteries in modern science. If dark matter truly forms the hidden skeleton of the cosmos, what is it actually made of? Because despite decades of observation, experiments, and theory, we still do not know. And the search for that answer has become one of the most fascinating scientific journeys of our time. The hidden halo around galaxies. When astronomers first realized that galaxies were rotating too fast, the discovery felt unsettling. The stars were behaving as if something massive surrounded them, yet nothing visible appeared in the telescopes. At first, the idea of invisible matter seemed almost like a temporary explanation, something scientists might discard once better observations arrived. But as the years passed, the evidence did not fade. It grew stronger. Every new measurement pointed to the same quiet conclusion. Galaxies were embedded inside enormous halos of unseen matter. To understand why astronomers began to picture galaxies this way, it helps to imagine the structure of a typical spiral galaxy. From a distance, a spiral galaxy looks like a glowing whirlpool of stars. The center forms a bright, dense bulge. Surrounding it is a flat rotating disk where spiral arms stretch outward like delicate ribbons of light. Inside those arms live billions of stars, drifting slowly through clouds of gas and dust. At first glance, it might seem that this luminous disk is the entire galaxy. But appearances can be deceptive. The glowing disk we see is only the visible portion of something much larger. Beyond the outer spiral arms, far beyond the last bright stars, astronomers began to detect signs of additional mass extending deep into space. This mass formed a kind of enormous sphere surrounding the galaxy, a halo. Unlike the halo of light sometimes seen around bright objects in photographs, this halo was completely invisible. It produced no light of its own. It reflected nothing. Yet its gravitational pull was unmistakable. Stars near the edges of galaxies moved as if they were being held in place by this vast surrounding mass. Without it, their orbits would not make sense. Imagine throwing a ball tied to a string. If the string is too short, the ball cannot move very far. But if the string is longer, the ball can travel in a much wider circle while still remaining attached. Dark matter halos act like that invisible string. They extend far beyond the visible stars, creating a much larger gravitational boundary for the galaxy. Inside that boundary, stars can move rapidly without escaping. Outside it, the galaxy's influence slowly fades into intergalactic space. Once astronomers began modeling galaxies with dark matter halos, something remarkable happened. Suddenly, the strange rotation curves made sense. The extra mass in the halo provided the additional gravity needed to keep outer stars moving quickly without flying away. What had once looked like a violation of gravity was actually a clue pointing toward hidden structure. The galaxy was simply much larger and much heavier than anyone had previously realized, and the visible stars represented only a small portion of its total mass. In fact, when scientists estimated the mass of these halos, the numbers were startling. In many galaxies, dark matter outweighed normal matter by a factor of 5 or more. That means the bright spiral arms we see in photographs represent only a thin luminous layer floating inside a far larger invisible system. It is almost like looking at a city at night from high above. You see glowing streets, bright buildings, clusters of lights marking neighborhoods. But those lights reveal only where activity happens. Beneath them lies a much larger foundation of roads, pipes, structures, and materials supporting the city itself. In the same way, the stars in a galaxy illuminate only the places where matter shines. The true gravitational structure lies beneath, hidden from view. And once astronomers accepted the idea of dark matter halos, they began to notice something else. These halos were not small. They were immense. For example, the visible disk of the Milky Way spans roughly 100,000 light-years. But the dark matter halo surrounding it may extend 300,000 light-years or more from the center. Some estimates suggest it could reach nearly halfway to the neighboring Andromeda galaxy. In other words, the Milky Way as we usually imagine it is only the glowing heart of a far larger invisible structure. Our entire solar system, drifting quietly within one of the galaxy's spiral arms, moves not only through the stars of the Milky Way but through a vast ocean of dark matter particles. They pass through us constantly, through the Earth, through the Sun, through every atom of our bodies. Yet we never notice them. They interact so weakly with ordinary matter that they slip through the universe almost like ghosts. Billions of them could pass through your hand every second without leaving the slightest trace. This strange property helps explain why dark matter remained hidden for so long. Telescopes rely on light, but dark matter does not produce light. Particle detectors rely on interactions, but dark matter barely interacts with normal matter at all. Its presence can only be inferred indirectly, through gravity, through the way stars move, through the bending of light, through the formation of galaxies themselves. And the more astronomers studied galaxies, the more it became clear that dark matter halos were not random. They followed patterns. Galaxies appeared to form inside regions where dark matter had already gathered. In the early universe, tiny fluctuations in the density of dark matter began pulling surrounding matter toward them. Those regions slowly grew larger. Gas collected inside them. Stars eventually ignited. Galaxies emerged. In this picture, dark matter came first. The galaxies we see today formed later, settling into the gravitational wells created by invisible halos. Which means that the structure of the visible universe was shaped long before the first stars ever began to shine. The hidden skeleton of the cosmos was already there, and galaxies simply grew along its framework. This idea has profound implications. Because if dark matter halos guide the formation of galaxies, then understanding them may reveal how the entire universe came to look the way it does today. Why galaxies form where they do. Why clusters gather in certain regions. Why enormous cosmic filaments stretch across millions of light years. All of these patterns may trace back to the quiet influence of dark matter, an invisible architecture guiding the evolution of the universe. And yet, despite everything astronomers have learned about these halos, one question still remains unanswered. What is dark matter actually made of? Because while we can map its gravitational influence, we still have no direct proof of its true nature. And solving that mystery has become one of the greatest scientific challenges of the modern era. Part 3: The Hidden Halo Around Galaxies. Segment 2:1:000 words. Once astronomers began to accept the idea that galaxies sit inside enormous halos of dark matter, a new question slowly emerged. Where did these halos come from in the first place? To answer that, scientists had to travel back in time, all the way to the beginning of the universe. Nearly 14 billion years ago, the universe was a very different place. There were no stars, no galaxies, no planets, only a vast, expanding ocean of extremely hot particles and radiation. In those early moments after the Big Bang, matter was spread almost perfectly evenly across space. The universe was remarkably smooth, like a calm surface of water stretching in every direction. But it was not completely uniform. Tiny fluctuations existed, incredibly small variations in density. Some regions were just a little bit denser than others. At first, those differences were almost unimaginably small. But gravity has a very patient nature. Over time, even the smallest imbalance can grow. Regions that were slightly denser began pulling more matter toward themselves. As they gathered more mass, their gravitational pull became stronger, drawing in even more matter from the surrounding space. Slowly, almost imperceptibly, the smooth early universe began to develop structure. But there was a complication. Ordinary matter, the kind made of atoms, protons, and electrons, interacts strongly with radiation. In the early universe, radiation filled space with enormous energy. Photons constantly collided with charged particles, pushing them around and smoothing out their motion. This meant that normal matter could not easily collapse into dense structures right away. The radiation kept stirring everything up. Dark matter, however, behaved differently. Dark matter does not interact with radiation in the same way. It does not absorb light. It does not scatter photons. It simply feels gravity. And because of that, dark matter began forming clumps much earlier than ordinary matter could. These clumps became the first gravitational seeds of cosmic structure. You can imagine them as invisible pockets where gravity was slightly stronger than the surrounding regions. Over millions of years, these pockets slowly grew. Dark matter gathered into larger and larger concentrations. Eventually, enormous halos formed. Vast regions of gravitational influence spread throughout the young universe. Only later, when the universe cooled and radiation became less dominant, could ordinary matter begin to fall into these halos. Gas drifted into the dark matter wells. The gas compressed. Temperatures rose. And eventually, the first stars ignited. In this way, dark matter halos acted like cosmic cradles where galaxies could be born. Without them, the universe might have remained too smooth for galaxies to form at all. Gravity alone, acting only on visible matter, may not have been strong enough to create the complex structures we see today. Dark matter provided the missing ingredient, the hidden framework that allowed galaxies to emerge. And once astronomers began exploring this idea, they discovered that dark matter halos were not isolated structures. They were connected. Across the universe, dark matter gathered into an enormous network of filaments, knots, and clusters. Imagine stretching a spider web across the entire cosmos. The thin strands of that web would represent filaments of dark matter. At the points where many strands intersect, large concentrations of matter would form. These intersections became the birthplaces of galaxy clusters. Meanwhile, galaxies themselves formed along the filaments, tracing the lines of the invisible structure beneath them. This vast arrangement is known as the cosmic web. It spans the observable universe, connecting galaxies across distances of hundreds of millions of light years. When astronomers map the positions of millions of galaxies, the pattern becomes strikingly clear. Galaxies do not fill space evenly. Instead, they gather along enormous filaments. Between those filaments lie vast empty regions called cosmic voids, where very few galaxies exist at all. The visible universe, it turns out, resembles a gigantic sponge-like structure, or a three-dimensional web, and dark matter appears to form the underlying skeleton of that web. Computer simulations have played an important role in revealing this structure. Scientists create digital universes inside powerful computers, filling them with particles representing dark matter and ordinary matter. Then they allow gravity to shape the system over billions of simulated years. When dark matter is included in these simulations, something extraordinary happens. The cosmic web naturally appears. Filaments grow. Clusters form. Galaxies emerge in patterns that closely match what astronomers observe through telescopes. But when dark matter is removed from the simulation, the results look very different. The universe fails to form large structures. Galaxies remain scattered and weak. The elegant web-like architecture disappears. This comparison strongly suggests that dark matter plays a central role in shaping the universe. Without it, the cosmos would look far simpler and far emptier. The great clusters of galaxies might never have formed. The long filaments stretching across space might not exist. And the Milky Way itself, the galaxy we call home, might never have been born. It is a humbling realization. The stars that light up our night sky may owe their existence to a form of matter we cannot see, touch, or fully understand. Dark matter may have quietly guided the evolution of the universe for billions of years, acting as an invisible architect, shaping galaxies, organizing clusters, weaving the cosmic web across unimaginable distances. Yet despite its enormous influence, dark matter remains one of the greatest mysteries in modern physics. Astronomers know where it is. They know how much of it exists. They even know how it behaves under the influence of gravity. But the fundamental question still lingers in the background. What exactly is it? What kind of particle could fill the universe, pass through ordinary matter almost unnoticed, and yet exert such powerful gravitational influence? To answer that question, scientists have begun searching for dark matter in ways far beyond astronomy. Deep underground, inside particle accelerators, in some of the most sensitive detectors ever built. Because somewhere in the quiet darkness of the cosmos, the true nature of this invisible matter is waiting to be discovered. And when that discovery finally comes, it may transform our understanding of the universe once again. The more astronomers studied dark matter halos, the more they realized that these invisible structures are not simply passive clouds surrounding galaxies. They are dynamic. They move. They grow. They merge with one another over cosmic time. And through these slow interactions, they shape the evolution of the universe itself. In the early universe, dark matter existed in many small clumps scattered throughout space. Each of these clumps created a small gravitational well, pulling nearby matter inward. Over millions of years, these clumps slowly attracted one another. When two dark matter halos drifted close enough together, gravity would cause them to merge. The smaller halo would gradually be absorbed by the larger one, becoming part of its growing gravitational field. This process happened again and again. Small halos combined into larger ones. Those larger halos merged into even greater structures. And inside these expanding halos, galaxies began to form. Astronomers sometimes describe this process as hierarchical growth. The universe built itself step by step. Small structures first, then larger structures, then enormous ones. Over billions of years, dark matter halos grew into the massive gravitational environments that now host entire galaxy clusters. Inside those halos, galaxies occasionally collided and merged as well. When two galaxies pass close to each other, their mutual gravity can distort their shapes. Spiral arms stretch and twist. Stars are pulled into long streams. Eventually, the two galaxies may combine, forming a single larger galaxy. These events are called galactic mergers, and they are a natural part of cosmic evolution. But the key point is this: the mergers are driven largely by the behavior of dark matter halos. When two halos collide, the galaxies embedded inside them are pulled together as well. In other words, galaxies follow the motion of the invisible structures surrounding them. Once again, the visible universe appears to be guided by a hidden architecture. And this hidden architecture continues to influence galaxies even today. For example, astronomers have discovered that the motion of galaxies inside clusters depends strongly on the distribution of dark matter. Clusters of galaxies can contain hundreds or even thousands of individual galaxies orbiting a common center. Yet the gravity generated by those galaxies alone is far too small to hold the cluster together. Just as with individual galaxies, there must be a massive dark matter halo surrounding the entire cluster. This halo can extend millions of light years across. Its gravity binds the cluster together, preventing galaxies from drifting away into intergalactic space. Without that invisible mass, galaxy clusters would slowly disperse. The same pattern appears again and again across the cosmos. Galaxies sit inside dark matter halos. Galaxy clusters sit inside even larger halos. Superclusters of galaxies appear to follow enormous concentrations of dark matter along the filaments of the cosmic web. At every scale, visible structures trace the shape of invisible ones. It is almost as if the universe is built in layers, a hidden gravitational skeleton made of dark matter. And upon that skeleton, the luminous matter we can see, stars, nebulae, galaxies, all arranged along the framework provided by something we still cannot directly observe. Despite its invisibility, dark matter may account for the majority of matter in the universe. When scientists estimate the total amount of mass required to explain the motion of galaxies and clusters, they consistently find the same ratio: roughly 5 times more dark matter than ordinary matter. This means that everything familiar to us, every atom in every star, every planet, every cloud of gas, every living creature, represents only a small fraction of the total matter in existence. The rest is dark. And this realization can be strangely comforting in a quiet, philosophical way. When we look at the night sky, we often imagine that we are seeing the universe itself. But in truth, we are only seeing a thin layer of it, the glowing surface. Beneath that surface lies something deeper, a hidden foundation that holds galaxies together and shapes the largest structures in existence. The stars are the visible lights on a vast cosmic stage. But the stage itself is built from something invisible, something silent, something we are only beginning to understand. And yet, for all its influence, dark matter remains extraordinarily elusive. If it truly fills the halos around galaxies, then our own solar system is moving through it right now. As the Milky Way rotates, the Sun and its planets travel through the galaxy's dark matter halo at tremendous speed. The Earth, orbiting the Sun, passes through this invisible sea of particles every moment. Trillions of dark matter particles may be passing through your body right now, and yet you feel nothing. They leave no trace. They do not collide with atoms in the same way ordinary particles do. They simply pass through, ghost-like. This behavior suggests that dark matter interacts extremely weakly with normal matter. So weakly that detecting it directly has become one of the greatest experimental challenges in physics. To search for it, scientists have built incredibly sensitive detectors deep underground. These laboratories are shielded beneath mountains or buried far below the surface to protect them from cosmic radiation and other interference. Inside them, detectors wait quietly for the faintest sign that a dark matter particle might interact with ordinary matter. A tiny flash of light, a small vibration inside a crystal, a subtle release of energy. So far, these experiments have not yet provided a definitive detection, but they continue to grow more sensitive every year. Because if dark matter particles truly exist, they must occasionally interact with the ordinary matter around us. And when that interaction is finally observed, it will reveal something extraordinary. It will tell us what the invisible skeleton of the universe is actually made of. The discovery would mark a turning point in our understanding of physics. For now, though, the mystery remains. We know dark matter is there. We see its gravitational fingerprints everywhere, in galaxies, clusters, and the cosmic web itself. But its true nature still hides in the darkness, waiting quietly beyond the reach of our current knowledge. And in the next step of this journey, scientists began asking an even deeper question. If dark matter shapes galaxies and clusters, could it also bend the path of light itself? Because if gravity can distort space around massive objects, then enormous concentrations of dark matter might reveal themselves in an unexpected way, not by shining, but by bending the light of distant galaxies as it travels across the universe. Seeing the invisible with gravity. Sometimes the universe reveals its secrets not by what we can see, but by how it distorts what lies behind it. For centuries, astronomers relied on light to understand the cosmos. Telescopes collect faint photons from distant stars and galaxies, and from those delicate signals we build our picture of reality. But light can also be deceived. Its path through the universe is not always straight. If light passes near a massive object, the gravity of that object can bend the fabric of space itself. And when space bends, the path of light bends with it. This strange idea was first described in detail by Albert Einstein in his theory of general relativity. Einstein realized that gravity is not simply a force pulling objects together. Instead, massive objects warp the geometry of space and time around them. Planets orbit the sun not because they are pulled by an invisible rope, but because they follow the curved paths created by the sun's mass. Even light, which has no mass of its own, must follow these curved paths. When light travels through warped space, its trajectory bends. At first, this idea sounded almost impossible to test. The bending of light by gravity is incredibly subtle. Yet in 1919, during a total solar eclipse, astronomers made one of the most famous observations in the history of science. As the moon passed in front of the sun, it briefly blocked the sun's blinding light. This allowed astronomers to photograph stars that appeared very close to the sun's position in the sky. According to Einstein's theory, the sun's gravity should slightly bend the starlight passing near it. That means the stars would appear in slightly different positions than expected. When scientists analyzed the photographs, the stars were indeed shifted by exactly the amount Einstein had predicted. Light had been bent by gravity. And with that discovery, an entirely new way of observing the universe was born. Astronomers realized that gravity could act like a lens. Just as a glass lens bends light in a telescope, massive objects in space can bend the light from distant galaxies behind them. This effect is now known as gravitational lensing. In many cases, the bending is very small, but when the mass involved is enormous, such as a galaxy cluster containing hundreds of galaxies, the effect can become dramatic. Light from a distant galaxy traveling toward Earth may pass near such a cluster along the way. As it does, the cluster's gravity bends the path of the light. The image of the distant galaxy becomes distorted. Instead of appearing as a simple round or spiral shape, the galaxy may stretch into long arcs. Sometimes the image splits into multiple copies. In rare cases, the light forms a complete circle around the massive object in the foreground. This ring of light is called an Einstein ring, one of the most striking visual confirmations of general relativity. For astronomers studying dark matter, gravitational lensing became an incredibly powerful tool. Because lensing depends only on gravity, it does not matter whether the mass producing that gravity is visible or invisible. If the mass is there, it will bend light. And that means astronomers can use gravitational lensing to map the total mass of galaxies and clusters, including the dark matter within them. When scientists began applying this technique, the results were astonishing. Galaxy clusters turned out to be far more massive than their visible matter suggested. The lensing patterns revealed enormous concentrations of unseen mass surrounding and filling the clusters. The invisible halos inferred from galaxy rotation curves suddenly appeared again, now confirmed by an entirely different method. The same hidden mass that was keeping galaxies from flying apart was also bending the light of distant galaxies behind them. Two completely independent observations were pointing to the same conclusion. Dark matter was real, and it was everywhere. Astronomers began creating detailed maps of this invisible mass by analyzing how gravitational lensing distorted the shapes of distant galaxies. Even when the distortions were subtle, slight stretches or shears in the images, statistical analysis of thousands of galaxies could reveal the distribution of dark matter in the foreground. These maps showed vast concentrations of dark matter surrounding clusters and galaxies. But they also revealed something even more surprising. Dark matter was not spread evenly. It formed complex structures, dense clumps, extended halos, filaments connecting clusters across immense distances. The same cosmic web predicted by computer simulations began to appear in real observations. Invisible threads of mass stretching across the universe. Galaxies gathered along these threads like dew drops on spider silk. And through gravitational lensing, astronomers could finally begin to see the outline of this hidden skeleton. Not directly, but through the way it bends the light of everything behind it. The universe had found a way to reveal its invisible structure after all, not through light emitted by dark matter itself, but through the subtle distortions it leaves on the light traveling through space. And as scientists continued studying these distortions, they uncovered one of the most dramatic demonstrations of dark matter's existence ever observed. An observation that showed visible matter and dark matter separating from each other during a cosmic collision. A discovery that would leave little doubt that dark matter is something fundamentally different from ordinary matter. Because when two massive galaxy clusters collided, the invisible matter passed straight through, while the visible matter did not, and the aftermath of that collision would become one of the clearest windows into the hidden structure of the universe. As astronomers continued studying gravitational lensing, they began to notice that the distortions in distant galaxies could reveal something far more detailed than anyone expected. Not just the presence of dark matter, but its exact location. By carefully measuring how light from distant galaxies was stretched and warped, scientists could reconstruct maps of the invisible mass sitting between those galaxies and Earth. It is a delicate process. Each individual galaxy image might appear only slightly distorted. Perhaps its shape is stretched just a little more in one direction than another. On its own, that tiny change could easily be mistaken for the galaxy's natural shape. But when astronomers analyze thousands of galaxies across a wide region of the sky, patterns begin to appear. If many galaxies in the same area are stretched in the same direction, it suggests that gravity from a large concentration of mass is bending their light as it travels toward us. By combining these tiny distortions across entire fields of galaxies, astronomers can reconstruct the invisible mass responsible for them. The result is something remarkable. A map of dark matter itself. Not through light, not through radiation, but through gravity alone. When the first maps like this were created, they revealed enormous concentrations of dark matter surrounding galaxy clusters. Clusters that already appeared massive through visible observations suddenly became even larger in these gravitational maps. The dark matter halos surrounding them extended far beyond the visible galaxies. And inside those halos, the distribution of mass was far from smooth. Instead, it formed dense knots and extended regions where gravity was stronger than expected. This was exactly what the dark matter hypothesis predicted. But one observation in particular provided an especially powerful piece of evidence. An observation involving the collision of two galaxy clusters. When clusters collide, the event unfolds on a truly cosmic scale. Each cluster may contain hundreds of galaxies, enormous clouds of hot gas, and an even larger halo of dark matter. As the clusters approach each other, their galaxies move at incredible speeds, sometimes several million kilometers per hour. Eventually, the two clusters pass directly through one another. What happens during this collision reveals something fascinating about the nature of dark matter. Galaxies themselves are mostly empty space. The stars inside them are separated by enormous distances. Because of this, when galaxies collide, their stars rarely crash directly into one another. Instead, the galaxies pass through each other with relatively little disturbance. But the hot gas inside galaxy clusters behaves differently. Clusters contain vast clouds of superheated gas filling the space between galaxies. This gas makes up a large portion of the visible matter in the cluster. And unlike stars, gas clouds interact strongly with one another. When two clusters collide, these gas clouds slam together. The collision slows them down dramatically. Shock waves ripple through the gas, heating it even further. In images taken by X-ray telescopes, this hot gas glows brightly, marking the region where the collision has taken place. But what about dark matter? Dark matter does not interact with gas. It does not experience friction or collisions in the same way. So when two clusters pass through one another, the dark matter halos should continue moving almost unaffected. The gas slows down. The dark matter keeps going. And this is exactly what astronomers observed in one of the most famous cosmic collisions ever discovered. The event is known as the bullet cluster. The bullet cluster consists of two galaxy clusters that collided roughly 150 million years ago. From Earth, we see the aftermath of that collision frozen in time. When astronomers studied the cluster using X-ray telescopes, they observed enormous clouds of hot gas glowing brightly in the center of the system. This gas had slowed down during the collision. It marked the region where the two clusters had crashed into each other. But when scientists used gravitational lensing to map the mass of the system, something extraordinary appeared. The majority of the mass was not located in the hot gas. Instead, the mass was concentrated around the galaxies themselves, farther away from the center of the collision. In other words, the visible matter and the invisible matter had separated. The gas, which represents much of the normal matter in the cluster, had been slowed and left behind. But the dark matter halos had continued moving forward with the galaxies. The gravitational lensing maps showed that the largest concentrations of mass were located ahead of the gas clouds, exactly where the dark matter halos should be if they had passed through the collision almost unaffected. This observation was incredibly important. If the extra gravity in galaxy clusters were caused by ordinary matter that we simply could not see, it should have behaved like the gas. It should have slowed down during the collision. But it did not. Instead, it behaved as if it were made of particles that interact very weakly with normal matter. Particles that pass through collisions almost as if nothing happened. Just like the dark matter predicted by cosmological models. The bullet cluster became one of the clearest pieces of evidence that dark matter is not merely an error in our understanding of gravity. It appears to be a real substance. A form of matter that exists alongside ordinary matter but interacts with it in very limited ways. Through gravitational lensing, astronomers were able to see the invisible, not directly, but through the gravitational fingerprints it leaves on the universe. And once scientists understood how to read those fingerprints, they began discovering dark matter everywhere they looked. In galaxies, in clusters, along the filaments of the cosmic web stretching across the universe. The hidden skeleton of reality was slowly coming into focus. Yet even with these powerful observations, the deepest mystery remained unsolved. We could see where dark matter was. We could measure how much of it existed. We could observe how it shaped the structure of the cosmos. But we still did not know what it actually was. And answering that question would require looking not only through telescopes, but deep inside the world of particle physics. The discovery of gravitational lensing changed the way astronomers observe the universe. Before this, most astronomical observations depended entirely on light emitted by stars, galaxies, or glowing gas. If something did not produce light, detecting it became extremely difficult. But gravitational lensing provided a completely different method. Instead of relying on light from an object itself, astronomers could study how that object bends the light coming from something behind it. It was like learning about the shape of an invisible object by observing how it distorts the shadows around it. With enough observations, the hidden structure of the universe began to emerge more clearly than ever before. Large surveys of the sky revealed subtle patterns in the shapes of distant galaxies. In most images, galaxies appear as tiny elliptical smudges of light. Their shapes vary naturally, but when astronomers examined millions of them across vast regions of the sky, a quiet pattern began to appear. In certain areas, galaxies seemed slightly stretched in similar directions. Not dramatically. Just enough that the pattern could be measured statistically. This phenomenon is known as weak gravitational lensing. Unlike the dramatic arcs and rings seen in strong lensing around massive clusters, weak lensing produces only gentle distortions. But when analyzed carefully across huge numbers of galaxies, these small distortions reveal something profound. They trace the distribution of dark matter across enormous regions of the universe. Using weak lensing techniques, astronomers began creating some of the largest maps of dark matter ever produced. These maps show how dark matter is spread across cosmic space. They reveal dense clumps where galaxy clusters reside, long filaments connecting those clusters, and vast empty voids where little matter exists at all. In other words, they reveal the architecture of the cosmic web, the same invisible skeleton predicted by cosmological simulations. Seeing these maps for the first time was a remarkable moment for many scientists. For decades, dark matter had been inferred from motion, from stars orbiting galaxies too quickly, or galaxies moving within clusters. But now, gravitational lensing allowed astronomers to visualize the structure created by that hidden mass, not directly, but through its influence on light traveling across the universe. And the picture that emerged was both elegant and mysterious. The universe appears to be woven together by this invisible framework. Galaxies gather along the filaments of the web, clusters form where filaments intersect, and enormous empty regions, known as cosmic voids, lie between them. If you could somehow see dark matter directly, the universe might resemble a gigantic three-dimensional web of faint threads stretching across space. The glowing galaxies we observe would simply highlight the densest intersections of that web, small sparks of light tracing a much larger hidden structure. Yet even as these observations confirmed the existence of dark matter, they also deepened the mystery surrounding it. Because gravitational lensing tells us how much dark matter exists and where it is located, but it does not tell us what dark matter actually is. To answer that question, scientists began turning their attention toward the smallest scales of nature, into the strange and often counterintuitive world of particle physics. If dark matter behaves like a form of matter, then perhaps it is made of particles. Particles that do not emit light. Particles that rarely interact with ordinary matter. Particles that travel through the universe almost invisibly. For decades, physicists have proposed many possible candidates. Some of these hypothetical particles have names that sound almost like something from science fiction. WIMPs, axions, sterile neutrinos. Each of these ideas represents a possible explanation for the mysterious mass shaping the cosmos. One of the most widely discussed candidates is something called a WIMP, which stands for Weakly Interacting Massive Particle. The name describes the particle's most important property. It interacts extremely weakly with normal matter. If WIMPs exist, they would pass through atoms almost without interacting at all. Billions of them could pass through your body every second without you noticing anything. Yet they would still possess mass. And that mass would produce gravity. Exactly the kind of behavior needed to explain dark matter. Other candidates, like axions, or even stranger. Axions would be incredibly light particles, far lighter than electrons. Yet enormous numbers of them could exist throughout the universe, collectively producing the gravitational effects we observe. Physicists have developed complex experiments designed to search for these particles. Some detectors are buried deep underground, shielded from cosmic radiation by kilometers of rock. Others are placed in extremely cold environments, cooled to temperatures just above absolute zero. These detectors wait patiently for a rare event, a moment when a dark matter particle might interact with the detector's material, producing a tiny flash of energy. So far, none of these experiments has provided a definitive answer. But the search continues. Because discovering the true nature of dark matter would represent one of the most important breakthroughs in modern science. It would reveal what most of the matter in the universe is made of. It would reshape our understanding of particle physics. And it would help explain how the universe evolved into the complex structure we see today. For now, though, dark matter remains hidden. Its presence revealed only through gravity, through the motion of galaxies, through the bending of light, through the quiet architecture of the cosmic web. It is a strange situation. The majority of matter in the universe surrounds us constantly, yet we cannot see it, we cannot touch it, we cannot yet identify it. The universe, it seems, is built upon something profoundly mysterious. A vast invisible substance that quietly holds galaxies together. And if we are to understand the true nature of reality, we must eventually uncover what that substance really is. Because somewhere within the darkness surrounding every galaxy, the answer is waiting. The cosmic web, the universe's hidden skeleton. If you could somehow step far outside the Milky Way and look back at the universe from an impossible distance, the view might surprise you. At first, you might expect the universe to look like a scattered field of galaxies, each one floating independently in the vast darkness of space. But the real picture is very different. Galaxies are not evenly spread throughout the universe. They gather, they cluster, they follow enormous patterns stretching across distances so vast that the mind struggles to grasp them. Instead of random scatterings of light, the universe forms something much more intricate. A vast network of matter connecting galaxies across unimaginable scales. Astronomers call this structure the cosmic web. The name is not poetic exaggeration. When scientists map the positions of millions of galaxies, the result truly resembles a web. Long filaments of galaxies stretch across hundreds of millions of light years. Where several filaments intersect, enormous clusters of galaxies appear, containing hundreds or even thousands of individual galaxies bound together by gravity. Between these filaments lie enormous empty regions known as cosmic voids. These voids are some of the largest structures in the universe. They can span tens or even hundreds of millions of light years, yet contain very few galaxies at all. In some sense, the universe resembles a gigantic sponge, or a foam. Most of the matter lies along the thin walls and threads surrounding vast empty bubbles of space. And underlying this enormous structure is something we cannot see directly. Dark matter. It forms the invisible skeleton of the cosmic web. Long before galaxies began to shine, dark matter had already begun organizing itself into this network. In the early universe, tiny fluctuations in density caused dark matter to clump together in certain regions. Over time, gravity amplified these small differences. Regions that were slightly denser pulled in more dark matter from their surroundings. As they grew heavier, their gravitational influence became stronger. More matter flowed toward them. Slowly, these growing concentrations began connecting with one another. Filaments formed. Nodes appeared where several filaments intersected. These nodes would later become galaxy clusters. Meanwhile, the long filaments connecting them would become the pathways along which galaxies formed and traveled. This entire structure grew gradually over billions of years. And once normal matter began falling into these dark matter filaments, the visible universe began to appear. Gas flowed along the invisible threads of dark matter. Where the gas accumulated, stars ignited. Galaxies were born. In this way, the cosmic web became the blueprint for the large-scale structure of the universe. Galaxies did not form randomly. They formed along the hidden scaffolding created by dark matter. You can imagine the cosmic web as something like the framework of a building under construction. The steel beams come first. Once the framework exists, the walls, floors, and decorations can be added later. Dark matter provided those beams. The stars and galaxies we see today are the luminous walls built around them. Without the underlying framework, the universe might never have developed the complex structures we now observe. Instead, matter might have remained too evenly distributed to form galaxies at all. This idea was not immediately obvious. For a long time, astronomers did not realize that galaxies followed such enormous patterns. When early galaxy surveys were conducted, telescopes could observe only small portions of the sky. Galaxies appeared scattered almost randomly. But as surveys grew larger and more powerful, scientists began mapping the positions of thousands, then millions, of galaxies. And something remarkable appeared. When plotted on large three-dimensional maps, galaxies did not fill space evenly. They formed long chains and walls. Clusters appeared at intersections of these structures, and enormous voids opened between them. One of the earliest glimpses of this pattern came in the 1980s, when astronomers began creating large redshift surveys. By measuring how much the light from distant galaxies was stretched by the expansion of the universe, scientists could estimate their distance. With those distances, they could construct three-dimensional maps of galaxy positions. When these maps were first displayed, the pattern was astonishing. Instead of random scatterings, galaxies formed enormous sheets and filaments stretching across hundreds of millions of light years. Some of these structures were so large that they challenged the idea that the universe should look the same everywhere on large scales. Yet the patterns kept appearing. More surveys confirmed them. Larger maps revealed even greater structures. And behind all of them seemed to lie the gravitational influence of dark matter. Computer simulations helped scientists understand how this could happen. When researchers simulated a universe dominated by dark matter, they watched as gravity slowly pulled matter into filaments and clusters. The simulated universe began to look strikingly similar to the real one. Filaments stretched across space. Clusters formed at intersections. Voids opened between them. When the simulation was complete, the resemblance between the digital universe and the observed universe was remarkable. It was as if dark matter naturally wove the cosmos into this enormous web-like pattern. And within that web, galaxies formed like glowing beads along invisible threads. This realization changed our understanding of the universe in a profound way. Galaxies are not isolated objects drifting randomly through space. They are part of a much larger structure. A structure shaped by dark matter over billions of years. The cosmic web stretches across the observable universe. Filaments hundreds of millions of light years long connect clusters of galaxies across unimaginable distances. And somewhere within one of those filaments lies our own galaxy, the Milky Way. Our home in the cosmos is just one small part of this vast hidden network, a single luminous knot within the immense invisible skeleton of the universe. And once astronomers understood that this cosmic web existed, they began asking an even deeper question. If dark matter forms the structure of the universe itself, how exactly does it guide the formation of galaxies? Because the galaxies we see today did not simply appear. They grew slowly over billions of years, shaped by the gravitational wells created by dark matter. Understanding that process would reveal even more about how the universe evolved from a smooth sea of particles into the rich cosmic landscape we now observe. Once astronomers understood that the universe forms a vast cosmic web, another realization slowly followed. The web is not just a static structure. It is alive with motion. Galaxies do not simply sit quietly along these filaments. They move slowly through them, guided by the gravitational currents created by dark matter. You can think of the cosmic web almost like a system of rivers. Instead of water flowing through valleys, matter flows along the invisible channels formed by dark matter. Gas drifts along these filaments. Small galaxies travel along them. Over time, many of these galaxies migrate toward the dense intersections of the web. Those intersections become galaxy clusters, the largest gravitationally bound structures in the universe. This slow movement of matter along the cosmic web is sometimes described as cosmic flow. It happens over timescales so vast that it is almost impossible to imagine. A galaxy might take billions of years to drift from one region of the web toward a dense cluster. Yet over cosmic time, this gradual movement reshapes the universe. Clusters grow larger. Filaments become more defined. Voids expand as matter drains away from them. In a sense, the universe is still evolving even today. The cosmic web continues to shift, stretch, and reorganize itself under the quiet influence of gravity. Dark matter is at the center of this process. Because dark matter makes up most of the universe's matter, its gravitational pull dominates the formation of large structures. Ordinary matter, the kind made of atoms, follows wherever dark matter gathers. When a dark matter filament forms, gas begins to drift into it. As gas accumulates, it can cool and collapse under its own gravity. Eventually, stars ignite. Small galaxies appear. Over time, these galaxies merge with one another, growing into larger systems. In this way, dark matter acts like a cosmic guide. It creates the gravitational landscape in which galaxies are born and evolve. Without this invisible structure, the universe might look completely different. Galaxies might be rare. Clusters might never form. The night sky might contain only scattered islands of stars drifting alone through empty space. Instead, the universe developed a complex and interconnected structure. A structure that stretches across billions of light years. And yet, even though we cannot see dark matter directly, astronomers have found ways to observe its influence on the cosmic web. One of the most powerful tools for this is the study of intergalactic gas. Between galaxies lies enormous amounts of extremely thin gas, mostly hydrogen. This gas is so diffuse that it is nearly impossible to observe directly with ordinary telescopes. But when light from a very distant object, such as a quasar, travels through this gas on its way to Earth, something interesting happens. The gas absorbs specific wavelengths of that light. When astronomers examine the light from the quasar using a spectrograph, they see a series of dark absorption lines. Each line represents a cloud of hydrogen gas along the path of the light. This pattern is known as the Lyman alpha forest. By studying these absorption patterns, astronomers can map the distribution of gas across enormous distances. And because gas tends to collect along dark matter filaments, the Lyman alpha forest provides another indirect map of the cosmic web. When scientists compare these observations with computer simulations of dark matter structure, the match is remarkable. The distribution of gas follows the same filamentary network predicted by dark matter models. Once again, the invisible skeleton of the universe reveals itself through subtle clues. Through gravity, through gas, through the motion of galaxies themselves. Each new observation adds another piece to the puzzle. And with every piece, the picture becomes clearer. The universe is not simply a random scattering of galaxies. It is a vast interconnected system. Filaments stretching across space. Clusters forming at intersections. Voids expanding between them. All shaped by the quiet influence of dark matter. But there is another fascinating aspect of the cosmic web. Its largest structures are almost unimaginably enormous. Some filaments stretch for hundreds of millions of light years. Galaxy clusters may contain thousands of galaxies, each with billions of stars. And entire superclusters of galaxies can span regions so large that light itself takes hundreds of millions of years to cross them. Yet even these enormous structures are still only part of the observable universe. Beyond them lies more web, more filaments, more clusters and voids extending farther into space. The cosmic web may continue across the entire observable universe, linking galaxies across billions of light years. And within this immense network lies our own small corner of existence. The Milky Way sits inside a structure known as the local group, a small cluster of galaxies that includes Andromeda and dozens of smaller galaxies. The local group itself lies along a larger filament connecting several nearby galaxy groups. And that filament connects to even larger structures beyond it. From our perspective on Earth, these structures are almost impossible to perceive directly. We see only the stars of our own galaxy filling the night sky. But beyond them, hidden in the darkness, the cosmic web stretches across space. An invisible architecture holding the universe together. A skeleton made mostly of dark matter. Yet even after mapping this enormous structure, scientists still face the same fundamental mystery. We understand how dark matter behaves on large scales. We can see how it shapes galaxies and clusters. We can trace its influence across the cosmic web, but we still do not know what dark matter actually is. And solving that mystery may require exploring the universe in ways we have never attempted before. Because somewhere within the invisible threads of the cosmic web lies the answer to one of the deepest questions in modern science. What is the hidden substance that holds the universe together? When astronomers first began mapping the cosmic web, the scale of the structure was almost difficult to accept. The distances involved stretch far beyond anything we experience in everyday life. Even within our own galaxy, distances are enormous. Light from the nearest star beyond the Sun takes more than 4 years to reach Earth. The Milky Way itself spans about 100,000 light-years. But the cosmic web operates on a far larger stage. The filaments connecting clusters of galaxies can stretch hundreds of millions of light-years across space. Entire superclusters may contain thousands of galaxies spread across regions so large that light itself needs hundreds of millions of years to travel from one side to the other. And yet, these immense structures are still only small pieces of the observable universe. If you were able to zoom out far enough, the cosmic web might look almost like a gigantic three-dimensional foam. Thin walls and strands of matter surround enormous empty regions called voids. Inside the walls lie galaxies and clusters. Inside the voids, there is very little at all. These voids are among the largest known structures in the universe. Some stretch across regions larger than entire superclusters. In these areas, galaxies are rare. The universe there is quiet and dark. But even these vast empty spaces help reveal the structure of the cosmic web. Because as matter gathers into filaments and clusters, gravity slowly pulls it away from the surrounding regions. Over billions of years, the voids become emptier while the filaments become denser. The web sharpens itself. Gravity quietly reshapes the universe, emphasizing the invisible skeleton created by dark matter. And yet, despite its enormous scale, the cosmic web remains difficult to observe directly. Dark matter does not glow. It produces no radiation that telescopes can capture. Instead, astronomers must reconstruct the web through indirect observations, through the positions of galaxies, through the motion of clusters, through gravitational lensing, through faint signals hidden in the light traveling across the universe. One of the most powerful tools for studying this structure comes from surveys that map millions of galaxies at once. Modern telescopes equipped with sensitive detectors can measure the positions and distances of enormous numbers of galaxies. Projects such as the Sloan Digital Sky Survey have created some of the most detailed maps of the universe ever produced. These maps reveal intricate patterns of galaxy distribution stretching across vast regions of space. When scientists plot the positions of these galaxies in 3 dimensions, the cosmic web becomes visible. Long chains of galaxies appear, walls of galaxies stretching across hundreds of millions of light-years, dense clusters at the intersections, and large empty voids between them. The pattern is unmistakable. The universe is organized, not randomly scattered, but woven together into a structure that extends across unimaginable distances. What makes this even more remarkable is how closely these observations match theoretical predictions. Long before many of these galaxy surveys were completed, cosmologists had already begun creating computer simulations of the universe. These simulations start shortly after the Big Bang, when matter was distributed almost uniformly throughout space. Tiny fluctuations in density were introduced, similar to those measured in the cosmic microwave background. Then gravity was allowed to act on that matter over billions of simulated years. The results were astonishing. As the simulation progressed, dark matter began clumping together. Filaments formed. Clusters appeared. Voids expanded between them. By the time the simulated universe reached its present age, the structure looked strikingly similar to what astronomers observed through telescopes. The cosmic web emerged naturally from the physics of dark matter and gravity. This was one of the strongest confirmations that the dark matter model of the universe was on the right track. Without dark matter, the simulations produced a very different universe. Structures formed too slowly. Clusters remained too small. The elegant web-like architecture simply did not appear. But when dark matter dominated the gravitational behavior of the simulation, the universe organized itself into the complex structures we now observe. Filaments stretching across space. Clusters forming at intersections. Galaxies gathering along invisible threads. In this way, dark matter appears to act as the cosmic architect. It shapes the large-scale structure of the universe. It guides the formation of galaxies. It organizes matter into the vast patterns stretching across the cosmos. And yet, even with this growing understanding, a deeper mystery still remains. We can observe the influence of dark matter on enormous scales. We can see the cosmic web it creates. We can measure its gravitational pull across billions of light years. But we still do not know the fundamental nature of the substance itself. We do not know what particles make it up. We do not know how it was created in the early universe. We do not know whether it interacts with ordinary matter in ways we have not yet discovered. In other words, we can see the skeleton of the universe. But we do not yet know what the bones are made of. And that mystery has led scientists to explore some of the most unusual ideas in modern physics. Because if dark matter truly forms the hidden framework of reality, understanding it may require looking beyond the familiar particles that make up the visible world. It may require discovering entirely new forms of matter, particles that have never been observed before. Particles that drift silently through the universe, shaping galaxies and clusters without ever revealing themselves directly. Somewhere in that invisible sea of particles surrounding every galaxy, including our own, the answer may already be present, waiting quietly to be discovered. Simulating the invisible universe. For most of human history, our understanding of the universe came from simply looking up. Astronomers pointed telescopes toward the sky and recorded what they could see. Stars, planets, nebulae, and distant galaxies slowly revealed their secrets through careful observation. But dark matter introduced a new challenge. It could not be seen directly. It produced no light. And yet its influence appeared everywhere. In the rotation of galaxies, in the structure of galaxy clusters, and in the vast cosmic web stretching across the universe. To understand something invisible on such enormous scales, astronomers needed a new kind of tool. Not a telescope, but a universe they could experiment with. This is where computer simulations began to play an important role. A cosmological simulation is essentially a digital universe built inside a computer. Scientists begin by recreating the conditions of the early universe shortly after the Big Bang. They fill the simulated universe with particles representing matter, mostly dark matter, along with smaller amounts of ordinary matter. Each particle follows the same basic laws of physics that govern the real universe. Gravity pulls particles together. Matter moves in response to gravitational forces. Time advances step by step. At first, the simulated universe looks very simple. Matter is distributed almost evenly across space, with only tiny fluctuations in density. But those small differences are enough. Gravity slowly amplifies them. Regions that are slightly denser begin pulling in nearby matter. Those regions grow larger. More particles fall into them. Gradually, the smooth early universe begins developing structure. Dark matter clumps together first, forming the gravitational wells that will eventually host galaxies. As the simulation continues, something remarkable begins to appear. Filaments stretch across the digital universe. Clusters of matter form at their intersections. And between these growing structures, large empty regions open up. The same cosmic web seen in astronomical observations begins to emerge naturally inside the simulation. What makes this so powerful is that scientists can adjust the properties of the simulated universe. They can change the amount of dark matter. They can remove dark matter entirely. They can modify the laws governing particle interactions. By observing how these changes affect the simulated universe, researchers can test different theories about how the real universe evolved. When dark matter is included in the simulation, the results closely resemble the universe we observe through telescopes. Filaments connect clusters. Galaxies gather along invisible threads. Large cosmic voids appear between them. But when dark matter is removed from the simulation, the universe behaves very differently. Structures grow much more slowly. Clusters fail to reach their observed sizes. The elegant web-like pattern does not appear. Instead, matter remains more evenly spread, unable to organize itself into the vast structures we see today. This difference provides powerful evidence for the existence of dark matter. It suggests that dark matter played a crucial role in shaping the universe. Without it, the cosmos might never have developed the rich architecture we now observe. The night sky itself might look very different. Galaxies might be rare. Clusters might never have formed. The universe could remain a far simpler place. In many ways, simulations allow astronomers to perform experiments that would otherwise be impossible. We cannot rewind the real universe to observe its earliest moments. We cannot change the laws of physics to see what might happen. But inside a simulation, scientists can explore these possibilities. They can watch galaxies grow. They can follow the merging of dark matter halos. They can track the formation of the cosmic web over billions of simulated years. Some of the largest cosmological simulations ever created involve billions of particles representing dark matter. These digital universes are so detailed that researchers can zoom into individual galaxies while still observing the large-scale structure of the entire simulated cosmos. One of the most famous examples is the Millennium simulation, which modeled the evolution of the universe across a region hundreds of millions of light-years wide. As the simulation progressed, dark matter halos formed and merged, creating the same filamentary structures astronomers observe in real galaxy surveys. When ordinary matter was added into the simulation, galaxies began forming within those halos. Stars ignited. Galaxies gathered along the filaments of the cosmic web. The resemblance to the real universe was striking. For many scientists, it felt as though they were watching the universe build itself from its earliest moments. These simulations also revealed something fascinating about the way galaxies grow. Galaxies do not form all at once. Instead, they grow gradually through a process of accumulation and merging. Small galaxies form first. Over time, they collide and combine with one another. Their dark matter halos merge as well, forming larger gravitational structures. In this way, the universe evolves like a complex ecosystem. Small systems grow into larger ones. Structures merge, reshape, and reorganize over billions of years. And throughout this entire process, dark matter remains the dominant force guiding the evolution of large-scale structure. Yet even with the help of these powerful simulations, a fundamental question remains unanswered. Simulations can show how dark matter behaves. They can demonstrate how it shapes the universe. But they cannot tell us what dark matter actually is. The particles used in these simulations represent a theoretical form of matter whose exact nature is still unknown. And until scientists discover what dark matter is made of, our understanding of the universe will remain incomplete. The cosmic web may reveal the skeleton of the universe, but the true nature of that skeleton remains one of the deepest mysteries in modern science. And solving that mystery will require looking beyond astronomy, into the strange world of fundamental particles and forces that shape reality itself. As cosmological simulations became more powerful, scientists began noticing something fascinating about the way dark matter behaves over time. Dark matter does not simply gather into a few large structures and stop there. Instead, it forms a hierarchy of halos nested within halos. Large halos contain smaller halos. Those smaller halos may contain even tinier structures within them. The universe, in this sense, resembles a set of Russian nesting dolls. A galaxy like the Milky Way sits inside a massive dark matter halo. But inside that halo, there are also smaller clumps of dark matter, remnants of earlier halos that merged during the galaxy's formation. These smaller structures are known as subhalos. Some of them may host small satellite galaxies. Others contain little or no visible matter at all. Simulations suggest that our own galaxy should contain hundreds, perhaps even thousands, of these dark matter subhalos. Yet when astronomers look around the Milky Way, they see only a few dozen small satellite galaxies. This discrepancy became known as the missing satellites problem. For a while, it puzzled scientists. If simulations predicted many small dark matter halos, why did we observe so few small galaxies? Over time, researchers realized that many of those halos may simply be too small to form stars. Star formation requires gas to cool and collapse under gravity. In very small halos, this process may not happen efficiently. The gas may be heated by radiation from the early universe or blown away by supernova explosions. Without gas, no stars form. And without stars, those halos remain completely dark. They drift quietly through the galaxy's halo, invisible except for the gravitational influence they exert. This idea suggests that our galaxy could be surrounded by a swarm of dark matter structures we cannot see. Small gravitational pockets scattered throughout the Milky Way's halo. These invisible subhalos might occasionally reveal themselves through subtle effects. For example, they could slightly disturb the motion of stars or create faint distortions in stellar streams. Long trails of stars left behind by disrupted star clusters. By studying these delicate motions, astronomers may eventually detect the presence of otherwise invisible dark matter clumps. Simulations have also helped scientists understand how galaxies like the Milky Way form their familiar spiral shapes. In the early universe, galaxies were often irregular and chaotic. Mergers between small galaxies were common. Each merger brought new stars, gas, and dark matter into the growing galaxy. Over billions of years, these chaotic beginnings gradually settled into more stable structures. Gas within the galaxy cooled and collapsed into a rotating disk. Stars formed along spiral arms. Dark matter halos continued to grow as smaller halos merged into them. Eventually, galaxies developed the elegant spiral patterns we observe today. Even now, galaxies continue evolving. The Milky Way itself is slowly merging with several smaller satellite galaxies, and in about 4 billion years, it will collide with the Andromeda Galaxy, the nearest large spiral galaxy to our own. The two galaxies will gradually merge into a single, much larger galaxy. Their dark matter halos will combine as well, forming a new, even more massive halo surrounding the merged system. This kind of event is common in cosmic history. Galaxies grow through a long sequence of mergers and accretion, and dark matter halos guide the entire process. Without dark matter, galaxies would struggle to maintain their structure during these interactions. The gravitational wells created by dark matter help stabilize galaxies, allowing them to survive and grow through these cosmic encounters. Another insight from simulations involves the way dark matter moves within halos. Unlike gas or stars, dark matter particles do not collide with one another in ordinary ways. They pass through each other almost freely. This property allows dark matter halos to remain relatively smooth and stable even during violent cosmic events like galaxy mergers. When two galaxies collide, their stars pass through one another with relatively few direct collisions. The dark matter halos behave similarly. They overlap, merge, and eventually settle into a new, larger halo. Meanwhile, the gas within the galaxies may collide and shock, triggering bursts of star formation. In this way, dark matter shapes the gravitational environment in which visible matter evolves. It forms the invisible framework that supports the luminous structures we observe. Yet despite the success of these simulations in explaining cosmic structure, they also highlight the limits of our current knowledge. The simulations assume certain properties for dark matter particles. For example, many models assume dark matter is cold, meaning the particles move relatively slowly compared to the speed of light. This idea forms the basis of the cold dark matter model, which has become the standard cosmological model used in many simulations. Cold dark matter behaves in a way that naturally produces the cosmic web and hierarchical structure observed in the universe. But alternative possibilities exist. Some scientists have proposed warm dark matter, consisting of lighter, faster-moving particles. Others have suggested even more exotic possibilities, including self-interacting dark matter or particles that interact through unknown forces. Each of these possibilities would produce slightly different cosmic structures. By comparing simulations with real observations, astronomers can test which models best match reality. In this way, simulations act as a bridge between theory and observation. They allow scientists to explore how different kinds of dark matter would shape the universe. And by comparing those predictions with the actual cosmos, researchers hope to narrow down the true nature of the invisible matter surrounding us. But even the most detailed simulation cannot fully solve the mystery. Because simulations are built from assumptions, they rely on theoretical particles that have not yet been directly observed. To truly understand dark matter, scientists must eventually detect the particles themselves. And that search has led researchers far beyond the realm of astronomy. Deep underground laboratories, sensitive particle detectors, powerful accelerators probing the smallest components of reality. Somewhere in these experiments, physicists hope to catch the first direct glimpse of the particles that make up the hidden skeleton of the universe. And when that moment arrives, it may finally reveal what most of the matter in the cosmos is truly made of. Even though cosmological simulations have become incredibly detailed, they are still, in a sense, experiments of imagination. Scientists begin with a set of assumptions about the universe. They choose the properties of dark matter, define how gravity behaves, and then allow the simulated universe to evolve over billions of virtual years. When the results resemble what astronomers observe through telescopes, it suggests that the assumptions are close to reality. But if the simulated universe looks very different, something in the model must be wrong. This constant comparison between simulation and observation has become one of the most powerful tools in modern cosmology. It allows researchers to test different ideas about dark matter and see how each possibility would shape the universe. For example, one key property scientists investigate is how quickly dark matter particles move. If dark matter particles move slowly, the idea behind cold dark matter, they can clump together efficiently under gravity. Small structures form first. These structures merge over time, building larger and larger halos. This naturally produces the hierarchical growth of cosmic structure seen in many simulations. But if dark matter particles moved much faster, the outcome would be very different. Fast-moving particles would spread out more easily, smoothing out small fluctuations in density. In that case, the smallest structures might never form at all. Galaxies might appear fewer in number, and the cosmic web might look much smoother. By comparing these predictions with real observations, scientists can narrow down the possible properties of dark matter. So far, the cold dark matter model has matched observations remarkably well. It reproduces the large-scale structure of the universe with impressive accuracy. Yet on smaller scales, some puzzles remain. For instance, simulations often predict that dark matter halos should have extremely dense centers. But when astronomers study the rotation curves of some small galaxies, the inner regions appear less dense than expected. This discrepancy has led scientists to explore variations in dark matter models. Some theories suggest that dark matter particles might interact with one another through forces other than gravity. These interactions could slightly redistribute the dark matter inside halos, producing density profiles closer to what astronomers observe. Other researchers propose that the difference may arise from the complex behavior of normal matter. Processes such as star formation, Supernova explosions and powerful stellar winds can push gas outward from galaxies. These energetic events may also alter the distribution of dark matter indirectly. In this way, the visible and invisible components of galaxies may influence one another more than we once believed. Simulations continue improving as scientists incorporate more detailed physics. Modern models track not only dark matter but also the behavior of gas, radiation, magnetic fields, and star formation. The result is an increasingly realistic picture of how galaxies grow and evolve. In some simulations, researchers can zoom into individual galaxies and watch spiral arms forming. Gas clouds collapse. Stars ignite. Black holes grow in the centers of galaxies. All of this unfolds within the gravitational environment created by dark matter halos. It is a remarkable achievement, a digital universe evolving according to the same physical laws that govern the real cosmos. And yet, despite the sophistication of these models, one truth remains clear. Simulations can only show us what happens if our assumptions are correct. They cannot confirm what dark matter actually is. For that, scientists must turn to experiments designed to detect dark matter particles themselves. If dark matter is made of particles, as many theories suggest, then those particles must occasionally pass through Earth. And if they pass through Earth, there is a chance that a detector could observe them. That possibility has inspired some of the most sensitive experiments ever built. Deep underground laboratories in places such as Italy, Canada, and the United States contain detectors shielded by layers of rock. The rock protects the instruments from cosmic rays and other sources of interference. Inside these laboratories, detectors sit in perfect darkness, cooled to extremely low temperatures. They wait patiently for the faintest sign of interaction. If a dark matter particle collides with an atom inside the detector, it might produce a tiny flash of light or a small vibration in a crystal. The signal would be incredibly subtle, so subtle that distinguishing it from background noise is extremely challenging. Yet scientists continue refining these experiments, making them more sensitive each year. At the same time, particle accelerators such as the Large Hadron Collider attempt to recreate conditions similar to those that existed shortly after the Big Bang. If dark matter particles can be produced in high-energy collisions, detectors might observe the energy they carry away. So far, no experiment has produced definitive evidence of dark matter particles. But the search continues. And every new experiment pushes the boundaries of what we can detect. In the meantime, astronomers continue mapping the cosmic web, observing galaxies, and studying the gravitational influence of dark matter across the universe. Together, these approaches form a powerful combination. Astronomy reveals where dark matter exists. Simulations show how it might shape the cosmos. And particle physics searches for the particles that could explain its nature. Step by step, these efforts bring us closer to understanding the invisible skeleton of the universe. A structure that surrounds every galaxy, including our own. A structure that has shaped cosmic history from the earliest moments after the Big Bang. And yet, despite everything we have learned, the true identity of dark matter remains one of the greatest mysteries in science. Somewhere in the quiet darkness of space, the answer is waiting. And when it is finally discovered, it may transform our understanding of reality itself. What dark matter might be? Segment 1-1-000 words. Up to this point, the evidence for dark matter has come from gravity. Galaxies rotate too quickly. Clusters contain far more mass than visible matter can explain. Light from distant galaxies bends around enormous halos of invisible matter. Across the universe, the cosmic web stretches through space, guided by something we cannot see. All of these observations point toward the same quiet conclusion. There is far more matter in the universe than the matter we know. Yet despite decades of study, one question remains unanswered. What is dark matter actually made of? For centuries, the concept of matter seemed simple. Everything around us is built from atoms. Atoms consist of protons and neutrons surrounded by electrons. Those particles combine to form molecules, planets, stars, and galaxies. But dark matter appears to be something entirely different. If dark matter were made of ordinary atoms, astronomers would see its presence in other ways. It would absorb light. It would emit radiation. It would interact with gas clouds and dust. But none of these signals appear. Instead, dark matter behaves as though it interacts with the universe almost exclusively through gravity. This unusual behavior suggests that dark matter may consist of particles that have never been observed before. Particles that do not participate in the familiar forces that shape ordinary matter. To explore this possibility, scientists turned to particle physics, the field that studies the smallest building blocks of nature. Over the past several decades, physicists have proposed many different candidates for dark matter. Each one attempts to explain how an invisible form of matter could fill the universe while remaining so difficult to detect. One of the earliest and most widely studied candidates is something called a WIMP. The name stands for Weakly Interacting Massive Particle. Although the name may sound technical, the idea behind it is relatively simple. A WIMP would be a particle that has mass but interacts only through gravity and the weak nuclear force. The weak nuclear force is one of the four fundamental forces of nature, alongside gravity, electromagnetism, and the strong nuclear force. Unlike electromagnetism, which governs light and electrical interactions, the weak force acts only over extremely short distances. If dark matter particles interact primarily through this weak force, they would rarely collide with ordinary matter. Most of the time, they would simply pass through atoms without interacting at all. This behavior matches the properties we expect from dark matter: invisible, massive, and extremely difficult to detect. WIMPs also have an appealing property from a theoretical perspective. Calculations suggest that if such particles were produced in large numbers during the early universe, their remaining abundance today would naturally match the amount of dark matter astronomers observe. This coincidence is sometimes called the WIMP miracle. It suggests that particles with the right properties could have formed during the Big Bang and persisted until the present day. For many years, this idea guided much of the experimental search for dark matter. Scientists built detectors specifically designed to capture the rare interactions that WIMPs might produce. Deep underground laboratories began searching for faint signals of these particles colliding with atoms. Particle accelerators attempted to create them in high-energy collisions. Yet despite decades of effort, no confirmed detection of WIMPs has been made. This does not mean they do not exist. It simply means that if they do exist, they interact even more weakly than scientists originally expected. Or perhaps their masses lie outside the ranges explored by current experiments. Because of these uncertainties, physicists have also explored other possibilities. Another intriguing candidate is a particle known as the axion. Axions were originally proposed to solve a different problem in particle physics related to the strong nuclear force. But researchers soon realized that if axions exist, they might also make excellent dark matter particles. Unlike WIMPs, axions would be extremely light. Many trillions of axions could exist within a tiny volume of space. Yet collectively, their combined mass could account for the gravitational effects attributed to dark matter. Axions would interact with ordinary matter even more weakly than WIMPs. Detecting them requires incredibly sensitive experiments designed to measure subtle electromagnetic effects that axions might produce. Some of these experiments use powerful magnets and ultra-sensitive detectors to search for faint signals that could reveal the presence of axions passing through Earth. Other dark matter candidates are even more exotic. Some theories propose particles known as sterile neutrinos, which interact even more weakly than ordinary neutrinos. Others suggest entire families of hidden particles existing in what physicists call a dark sector, a parallel set of particles and forces that rarely interact with our familiar matter. In these models, dark matter could be part of a hidden world that coexists with our own, influencing the universe through gravity while remaining largely invisible to our instruments. At the moment, all of these ideas remain possibilities. None has yet been confirmed, but each represents a different way of explaining the invisible mass shaping the universe. And as scientists continue exploring these possibilities, the search for dark matter has become one of the most exciting challenges in modern physics. Because discovering the true nature of dark matter would answer one of the deepest questions about the universe. It would reveal what most of the matter in existence is actually made of, and it would transform our understanding of how the cosmos came to look the way it does today. Somewhere among these possibilities, WIMPs, axions, sterile neutrinos, or something even stranger, the answer may already exist, waiting quietly in the darkness that surrounds every galaxy. What dark matter might be? As scientists explored the possibility that dark matter might consist of new particles, they began designing experiments that could search for these particles directly. The challenge was enormous. If dark matter interacts only weakly with ordinary matter, then detecting it would require instruments capable of sensing incredibly small signals. Signals so faint that even the slightest background noise could hide them. To overcome this problem, many dark matter experiments are located deep underground. Far below the surface of the Earth, layers of rock help shield detectors from cosmic radiation and other energetic particles constantly arriving from space. Inside these underground laboratories, detectors sit quietly in carefully controlled environments. The air is purified. Temperatures are often lowered to extremely cold levels. The instruments themselves are surrounded by layers of shielding designed to block any stray radiation. All of these precautions exist for one purpose: to create a place quiet enough that the smallest possible interaction might finally be noticed. Imagine sitting in a silent room, listening for the faintest whisper. That is essentially what these experiments are doing. They are waiting for the moment when a dark matter particle might collide with an atom inside the detector. Such a collision would release a tiny amount of energy, perhaps a flash of light, perhaps a slight vibration in a crystal, perhaps a tiny electrical signal. Any one of these could indicate that a dark matter particle had passed through the detector. Experiments such as xenon, lux, and Panda X use tanks filled with liquid xenon, a dense noble gas that is extremely sensitive to tiny particle interactions. When a particle collides with a xenon atom, the interaction produces a brief flash of light and a small electrical signal. By measuring both signals carefully, scientists can determine whether the event might be caused by a dark matter particle. Other experiments use crystals cooled to temperatures just above absolute zero. At these temperatures, even a minuscule interaction can produce a measurable vibration within the crystal lattice. These vibrations are so subtle that detecting them requires sensors capable of measuring extremely small changes in energy. For years, scientists have monitored these detectors, hoping to catch the telltale sign of a dark matter interaction. Occasionally, experiments report intriguing signals, but so far, none has been confirmed as a definitive detection. The signals could still be explained by other sources, such as background radiation or rare particle interactions unrelated to dark matter. Despite this, the sensitivity of these experiments continues to improve. Each new generation of detectors becomes larger and more precise. The search area expands. The silence grows deeper, and the possibility of discovery becomes more real. At the same time, particle physicists have pursued another approach. If dark matter particles were created during the early universe, perhaps they can also be created artificially in high-energy particle collisions. This idea is one reason the Large Hadron Collider, located near Geneva, Switzerland, has attracted so much attention. Inside the collider, particles are accelerated to enormous speeds and smashed together with tremendous energy. These collisions recreate conditions similar to those that existed fractions of a second after the Big Bang. If dark matter particles can be produced in these collisions, they might appear indirectly in the experimental data. Because dark matter interacts so weakly with ordinary matter, the particles would escape the detectors without leaving a visible trace. But their presence could still be inferred. Physicists carefully measure the energy and momentum of particles produced in the collision. If some energy appears to be missing, carried away by an invisible particle, it could be a sign that dark matter has been created. So far, experiments at the Large Hadron Collider have not yet found definitive evidence for dark matter particles. But the search continues. New upgrades to the accelerator and its detectors may allow scientists to explore even higher energies and rarer events. Beyond underground detectors and particle accelerators, astronomers have also searched for indirect signals of dark matter in space. If dark matter particles occasionally collide with one another, those collisions might produce high-energy radiation that telescopes could detect. Some observatories look for unusual gamma-ray signals that could indicate dark matter interactions occurring in the centers of galaxies. Others search for subtle patterns in cosmic rays that might reveal the presence of dark matter particles. These observations remain inconclusive for now, but each new experiment helps narrow the possibilities. It tells scientists which theories are less likely, and which remain plausible. The search for dark matter has therefore become a truly global effort. Astronomers study the structure of the universe. Physicists build detectors deep underground. Particle accelerators recreate the earliest moments of cosmic history. Together, these approaches form a vast scientific investigation, one that stretches from the smallest particles to the largest structures in the universe. And somewhere within this effort lies the answer to one of the most profound questions in modern science. What is the invisible substance that fills the halos of galaxies, shapes the cosmic web, and holds the universe together? For now, the answer remains hidden. But with each experiment, each observation, and each new idea, we move a little closer to understanding the true nature of dark matter. And when that discovery finally arrives, it may reveal an entirely new layer of reality beneath the universe we thought we knew. As the search for dark matter continues, one quiet realization has slowly taken shape among scientists. Dark matter might not be a single thing. It could be an entire family of particles. Just as ordinary matter contains many different kinds of particles, electrons, quarks, neutrinos, and others, dark matter might also belong to a much richer hidden world. Physicists sometimes refer to this possibility as the dark sector. In this idea, the universe contains not just the familiar particles we know, but also a parallel set of particles that interact mostly with one another. These particles might have their own forces, their own interactions, and perhaps even their own complex structures. But because they interact so weakly with ordinary matter, we cannot see them directly. Their presence would be revealed mainly through gravity. If such a dark sector exists, the universe might be far more complex than we once imagined. Most of the matter in existence could belong to this hidden realm. A vast population of particles moving quietly through the cosmos, shaping galaxies and clusters while remaining invisible to our instruments. The idea may sound unusual, but modern physics already suggests that nature may contain many particles beyond the ones we currently know. The Standard Model of particle physics, which describes the known fundamental particles, has been remarkably successful. It explains how atoms are built and how particles interact through the electromagnetic, weak, and strong forces. Yet even this powerful theory leaves many questions unanswered. For example, the Standard Model does not explain dark matter. It does not explain why the universe contains more matter than antimatter. And it does not unify gravity with the other fundamental forces. Because of these unanswered questions, many physicists believe that the Standard Model is only part of a deeper theory. Dark matter may be one of the first clues pointing toward that deeper structure. Some theories propose that dark matter particles may interact with one another through forces similar to those in ordinary matter. If this is true, dark matter might form structures within dark matter halos, small clumps, dense regions, perhaps even something like dark matter, atoms, bound together by unknown forces. These ideas remain speculative, but they demonstrate how the search for dark matter is expanding beyond a single particle candidate. Scientists are now exploring entire families of possibilities. each one offering a different explanation for the invisible matter shaping the cosmos. While physicists investigate these ideas on the smallest scales, astronomers continue searching for clues in the largest structures of the universe. Because the behavior of dark matter across cosmic distances may reveal important hints about its nature. For example, the way dark matter gathers inside galaxies can tell us whether the particles interact strongly with each other or only through gravity. If dark matter particles occasionally collide with one another, the internal structure of dark matter halos might look different. The centers of galaxies might be smoother and less dense. Clusters of galaxies might behave differently during collisions. Astronomers carefully study these patterns, comparing them with predictions from different dark matter models. So far, most observations suggest that dark matter interacts very weakly, if at all, with itself or with ordinary matter. This is one reason why it remains so difficult to detect directly. But the possibility of subtle interactions has not been ruled out, and even small differences in behavior could provide important clues. Meanwhile, new telescopes and observatories are beginning to explore the universe with unprecedented precision. Large sky surveys are mapping the positions of billions of galaxies. Gravitational lensing measurements are becoming more detailed. Future observatories such as the Vera C. Rubin Observatory and the Euclid Space Telescope will map the distribution of dark matter across enormous regions of the universe. These observations may reveal new patterns in the cosmic web, patterns that could help distinguish between different theories of dark matter. In this way, the search for dark matter continues on many fronts at once. Underground detectors waiting for rare particle interactions. Particle accelerators recreating the energy of the early universe. Astronomers mapping the large-scale structure of the cosmos. Computer simulations testing new ideas about invisible matter. Each of these approaches explores a different piece of the puzzle, and together they form one of the most ambitious scientific efforts ever undertaken. Because understanding dark matter means understanding most of the matter in existence. It means uncovering the hidden framework of the universe itself. The stars we see in the night sky are only the bright surface of reality. Beneath them lies a much larger structure, an invisible ocean of matter filling galaxies, clusters, and the cosmic web. And somewhere within that vast invisible ocean lies the answer to a question that has fascinated scientists for decades. What exactly is the substance that holds the universe together? For now, the answer remains hidden. But every observation, every experiment, and every new idea brings us one step closer. And perhaps one day, the invisible skeleton of reality will finally reveal its true form. The cosmic web. Imagine drifting far above the universe. Not just above a single planet, or even above a galaxy, but far enough away that you could see the largest structures in existence. From that distance, the universe would not appear random. It would not look like a chaotic scattering of galaxies across empty space. Instead, it would resemble something strangely familiar. A web. A vast network of filaments stretching across unimaginable distances. Thin strands of matter connecting enormous clusters of galaxies. Between these strands lie immense regions of emptiness, cosmic voids that contain very few galaxies at all. This enormous pattern is known as the cosmic web. It is the largest structure in the universe, and at its foundation lies dark matter. The cosmic web did not appear suddenly. It began forming shortly after the universe itself was born. In the earliest moments after the Big Bang, the universe was incredibly hot and dense. Matter and radiation were mixed together in a glowing plasma. Tiny fluctuations existed within this plasma, slight variations in density that had been imprinted during the earliest moments of cosmic history. These fluctuations were incredibly small, differences of only a few parts in 100,000. Yet over billions of years, gravity slowly amplified them. Regions that were slightly denser than average began attracting more matter. And as more matter gathered, gravity became stronger in those regions. This process created a gradual separation between dense areas and emptier ones. Dark matter played a crucial role in this transformation. Because dark matter does not interact with light, it was able to begin clumping together earlier than ordinary matter. While normal matter was still interacting with radiation in the early universe, dark matter was already responding to gravity. Slowly, almost silently, it began forming the first gravitational scaffolding of the cosmos. Over time, these invisible structures grew larger. Small clumps merged into bigger halos. Halos connected through filaments. Filaments stretched across enormous distances, linking clusters of galaxies together. And inside these dark matter structures, ordinary matter followed. Gas flowed along the gravitational pathways created by dark matter. Where enough gas accumulated, stars formed. Where stars gathered, galaxies were born. In this way, dark matter shaped the architecture of the universe long before the first stars ever ignited. Today, when astronomers map the distribution of galaxies across the sky, they see the imprint of this hidden structure. Galaxies do not appear randomly scattered. Instead, they trace out the same enormous web predicted by simulations of dark matter. Clusters of galaxies sit at the intersections of filaments. Long strands of galaxies stretch between them, and vast empty voids fill the spaces in between. It is as though the visible universe has grown along the skeleton provided by dark matter. The galaxies we observe are simply the glowing surface of a much larger invisible structure. Even more remarkable is the scale of the cosmic web. Individual filaments can stretch across hundreds of millions of light years. Clusters of galaxies can contain thousands of galaxies bound together by gravity. The voids between them can span even greater distances. Some of these empty regions measure more than 1 billion light-years across. From the perspective of a galaxy inside a filament, the surrounding universe might feel crowded with neighboring galaxies. But if you could travel into one of the great cosmic voids, the night sky would look very different. Galaxies would appear extremely distant and sparse. The nearest large galaxy might be hundreds of millions of light-years away. In these regions, the universe becomes a place of extraordinary emptiness. And yet even these vast voids are part of the cosmic web. They exist because matter has flowed outward toward the denser filaments and clusters. Gravity pulls matter into structures, leaving emptiness behind. Astronomers have spent decades mapping this enormous pattern. Large sky surveys have catalogued millions of galaxies, measuring their positions and distances. By connecting these measurements, scientists can create three-dimensional maps of the universe. When viewed together, these maps reveal the same intricate web predicted by dark matter simulations. It is one of the most powerful confirmations that dark matter truly exists. Because without dark matter, the cosmic web would look very different. Ordinary matter alone would not have formed such large structures so quickly. The early universe would have remained smoother for much longer. Galaxies would have formed later, and the large-scale pattern of the universe would be less pronounced. But the universe we observe is rich with structure. Clusters, filaments, voids, all arranged in a pattern that stretches across billions of light-years. A pattern shaped by something we cannot see. Dark matter does not shine. It does not emit light or heat. And yet its gravitational influence has sculpted the universe on the grandest scales imaginable. Every galaxy, including our own Milky Way, is part of this enormous cosmic web, a web whose threads extend far beyond anything the human mind can easily grasp. And somewhere within this immense structure lies the quiet framework that holds the universe together. Although the cosmic web stretches across billions of light-years, its structure follows surprisingly simple rules. Gravity pulls matter toward regions that are already slightly denser than their surroundings. Over immense spans of time, this simple rule gradually transforms small differences into enormous structures. Imagine placing tiny ripples across a calm surface of water. At first, the ripples are barely noticeable. But if those ripples slowly attract more water toward them, they begin to grow. Small waves become larger waves. Patterns begin to form. In a similar way, The early universe contained extremely small variations in density, regions that were only slightly heavier than their surroundings. But gravity does not need dramatic differences to begin its work. Even the smallest imbalance can grow stronger over time. And in the young universe, there was plenty of time. Billions of years. During this long history, dark matter continued to collapse into increasingly complex structures. Small halos merged with other halos. Filaments thickened as more matter flowed toward them. Clusters of galaxies formed where multiple filaments intersected. These intersections are some of the most massive structures in the universe. Galaxy clusters can contain thousands of galaxies, along with enormous clouds of hot gas. All of this is held together by the gravitational influence of dark matter halos that surround the cluster. If we could somehow remove the dark matter from a galaxy cluster, the remaining matter would not stay bound for long. The galaxies would drift apart. The hot gas would slowly escape. The cluster would dissolve. But dark matter halos act like enormous gravitational anchors. They hold these vast systems together across cosmic time. Astronomers have even observed dramatic collisions between galaxy clusters. One of the most famous examples is known as the bullet cluster. In this event, two galaxy clusters passed through one another at tremendous speeds. When the clusters collided, the ordinary matter behaved differently from the dark matter. The gas within the clusters slammed together and slowed down, producing a huge cloud of extremely hot gas. But the dark matter halos passed through the collision almost unaffected. Because dark matter interacts so weakly with itself and with ordinary matter, the halos continued moving forward. Astronomers were able to map this separation using gravitational lensing. The result was extraordinary. The regions containing most of the mass were no longer aligned with the visible gas clouds. Instead, the mass appeared to be located in invisible halos that had moved ahead of the gas. This observation provided one of the strongest pieces of evidence that dark matter truly exists. It showed that the gravitational mass in the clusters could not be explained by visible matter alone. Something invisible was clearly carrying most of the mass, and that invisible matter had passed through the collision almost as if nothing had happened. Events like the bullet cluster allow scientists to test how dark matter behaves under extreme conditions. If dark matter interacted strongly with itself, the halos would have slowed down during the collision. But observations show that the halos moved through one another with very little resistance. This suggests that dark matter particles rarely collide with one another. Their interactions appear to be dominated almost entirely by gravity. Even in these violent cosmic events, dark matter remains strangely ghost-like. Meanwhile, along the vast filaments of the cosmic web, galaxies continue their slow journeys through space. Over billions of years, galaxies drift along these gravitational pathways. Some fall into clusters. Others merge with neighboring galaxies. Occasionally, two galaxies collide and combine, forming a new, larger system. These mergers are a natural part of cosmic evolution. They help build the massive galaxies we observe today. Our own Milky Way has experienced many such mergers throughout its history, and in several billion years, it will likely merge with the nearby Andromeda galaxy. Even these galactic encounters are influenced by dark matter. The halos surrounding galaxies extend far beyond the visible stars. When two galaxies approach each other, their halos interact long before the stars themselves come close. The gravitational pull of these halos shapes the motion of the galaxies, guiding them toward eventual collision. In this way, dark matter silently orchestrates many of the grand events in cosmic history. It governs the formation of galaxies. It shapes the motion of clusters. It guides the flow of matter along the filaments of the cosmic web. Yet despite its enormous influence, dark matter remains invisible. Astronomers can map its presence through gravitational effects, but the substance itself remains hidden. Still, by studying the structure of the cosmic web, scientists continue learning more about the role dark matter plays in shaping the universe. Every filament, every cluster, and every vast cosmic void tells part of the story. A story of gravity slowly sculpting structure across billions of years. And behind it all, the quiet presence of dark matter guiding the architecture of the cosmos. When astronomers began mapping the large-scale structure of the universe, they expected to find patterns. But few anticipated just how intricate those patterns would be. As galaxy surveys expanded and telescopes grew more powerful, scientists started building three-dimensional maps of where galaxies actually sit in space. Instead of simply looking at the sky as a flat picture, they measured the distances to galaxies and placed them within a vast cosmic map. What emerged from those maps was something astonishing. Galaxies gathered along enormous threads that stretched across hundreds of millions of light years. These threads intersected at massive nodes, where galaxy clusters formed. Between the threads lay enormous empty regions known as cosmic voids. The universe looked less like scattered islands of stars, and more like a delicate lacework woven through space. This pattern appeared again and again, no matter how far astronomers looked. It appeared in surveys of nearby galaxies. It appeared in maps of distant galaxies whose light had traveled for billions of years. And it appeared in computer simulations that modeled the evolution of dark matter. The resemblance between these maps and the simulations was striking. In simulations, dark matter collapsed into filaments that connected clusters across vast distances. Gas then flowed along these filaments, feeding the growth of galaxies. When astronomers compared the simulated maps to the real universe, the structures looked remarkably similar. This agreement between theory and observation became one of the strongest pieces of evidence that dark matter truly forms the scaffolding of the cosmos. It suggested that the universe we see today grew naturally from the gravitational collapse of dark matter over billions of years. The cosmic web is not static. It continues evolving even now. Galaxies slowly drift along the filaments toward denser regions. Clusters continue growing as they pull in surrounding matter. Over extremely long timescales, even larger structures may form as clusters themselves merge together. But this process unfolds so slowly that it is almost impossible to notice within a single human lifetime. The motions are measured in millions or billions of years. From our perspective on Earth, the cosmic web appears almost frozen in place. Yet within this quiet stillness, the universe remains gently in motion. Gas flows along filaments like rivers of intergalactic material. Galaxies travel through space under the influence of gravity. Dark matter halos merge and grow. All of this activity occurs across distances so vast that the scale becomes difficult to imagine. One filament of the cosmic web might span hundreds of millions of light years. Traveling from one end to the other at the speed of light would take longer than the entire history of human civilization. Even the Milky Way, enormous as it seems to us, is only a tiny part of this grand structure. Our galaxy sits within a modest filament known as the local sheet, which is part of a larger structure called the Laniakea supercluster. This immense region contains tens of thousands of galaxies, all slowly drifting toward a central gravitational region known as the Great Attractor. The Milky Way and its neighboring galaxies are slowly moving within this cosmic landscape. Our galaxy is not stationary. It is traveling through space at hundreds of kilometers per second as it follows the gravitational pathways of the cosmic web. And yet, because the universe is so large, these motions feel almost imperceptible from our vantage point. The night sky appears calm and unchanging. The stars rise and set. Constellations drift across the seasons. But behind that peaceful appearance lies a vast structure extending far beyond what the eye can see. A structure formed by dark matter over billions of years. Modern telescopes are beginning to observe the faint gas that lies along some of these cosmic filaments. This gas is extremely diffuse, far thinner than even the emptiest regions within galaxies. But with sensitive instruments, astronomers have detected subtle signals that reveal the presence of this intergalactic material. These observations help confirm what simulations predicted long ago. The cosmic web is real. Galaxies trace its brightest threads, but much of the matter within the web remains invisible. Dark matter forms the backbone. Gas flows along its gravitational channels. Stars ignite where enough material gathers. In this way, the cosmic web connects the smallest scales of galaxy formation with the largest structures in existence. It reveals how gravity has shaped the universe from its earliest moments until today. And perhaps most remarkable of all is the realization that everything we see, the stars, the planets, the glowing galaxies, makes up only a small fraction of the total matter within this web. Most of the mass belongs to dark matter, invisible, silent, yet responsible for shaping the grand architecture of the cosmos. The galaxies are like lanterns hanging from an enormous unseen framework. They illuminate only a tiny portion of the vast structure that surrounds them, and somewhere within that immense invisible framework lies the hidden skeleton of reality, a structure that has guided the growth of galaxies, clusters, and the cosmic web itself since the earliest days of the universe. The limits of what we know. After decades of observation, measurement, and theory, scientists have become increasingly confident about one thing. Dark matter exists. Its gravitational fingerprints appear everywhere, in the motion of galaxies, in the bending of light across cosmic distances, in the delicate structure of the cosmic web, in the ancient patterns preserved in the faint glow of the cosmic microwave background. All of these clues point toward the same quiet conclusion. Most of the matter in the universe is invisible. And yet, despite this overwhelming evidence, there is something deeply humbling about the situation. We know dark matter is there, but we still do not know what it is. In a way, modern cosmology finds itself in a curious position. Astronomers can map the distribution of dark matter across billions of light years. They can measure how it shapes galaxies and clusters. They can simulate its influence on the growth of the universe. But when it comes to the fundamental nature of dark matter itself, the answer remains hidden. This is one of the great mysteries of modern science. And it reminds us that even as our understanding of the universe grows, new questions often appear just beyond the horizon. To appreciate how unusual this situation is, it helps to think about how science usually works. Typically, scientists discover a new phenomenon and gradually uncover its underlying mechanism. Electricity, for example, was observed long before its nature was understood. People noticed static sparks and strange forces long before the discovery of electrons. But eventually, experiments revealed the particles and interactions responsible for those effects. With dark matter, the process has been almost reversed. We have seen the effects first. The gravitational influence, the structure of galaxies, the formation of cosmic filaments. But the particles responsible remain invisible. It is as though we are watching shadows move across a wall without seeing the object casting them. This unusual situation has led some scientists to ask an even deeper question. What if dark matter does not exist at all? What if the strange gravitational effects we observe are not caused by unseen matter, but by a misunderstanding of gravity itself? This idea has inspired alternative theories of gravity. One of the most well-known is called modified Newtonian dynamics, or MOND. MOND proposes that the laws of gravity might behave slightly differently at extremely low accelerations. In regions such as the outer edges of galaxies, where gravitational forces are very weak, the behavior of gravity might change. If that were true, it could potentially explain the flat rotation curves of galaxies without requiring dark matter halos. The idea is intriguing, and in some cases, modified gravity models can reproduce certain observations surprisingly well. But when scientists examine the universe on larger scales, these theories begin to encounter difficulties. For example, the cosmic microwave background contains patterns that match the predictions of dark matter models extremely well. Galaxy clusters contain far more mass than visible matter alone can explain. And events like the bullet cluster show clear separations between ordinary matter and the gravitational mass inferred from lensing. These observations are difficult to explain without invoking dark matter. As a result, most scientists believe that dark matter is real. Still, alternative ideas continue to be explored, because questioning assumptions is a central part of scientific progress. And sometimes, the most surprising discoveries arise from unexpected directions. Another possibility is that dark matter exists, but behaves differently from what current models assume. Perhaps dark matter particles interact more strongly with one another than expected. Perhaps they decay over extremely long periods of time. Or perhaps they belong to an entirely new category of particles that current theories have not yet fully described. Each of these possibilities opens new avenues of research, new experiments, new observations, new ways of thinking about the universe. Meanwhile, astronomers continue collecting more precise data about the cosmos. Every new telescope brings clearer images of distant galaxies. Every new sky survey maps larger regions of space. Every new experiment refines our understanding of cosmic structure. The universe itself becomes the ultimate laboratory, a place where gravity has been running experiments for billions of years. By studying the results of those cosmic experiments, scientists hope to uncover the true nature of dark matter. But even as we search for answers, the mystery itself carries a certain beauty. It reminds us that the universe is still full of unknowns. That despite centuries of scientific discovery, we are still only beginning to understand the deeper layers of reality. The stars above us may feel familiar, but the invisible matter surrounding them remains one of the greatest puzzles in existence. A puzzle waiting patiently for the moment when the right idea, the right observation, or the right experiment finally reveals the truth hidden in the darkness. Science often moves forward in small steps. A new observation leads to a new idea. A new idea leads to an experiment. The experiment produces results, which either confirm the idea or force scientists to rethink their assumptions. Over time, this quiet process gradually builds our understanding of the universe. But occasionally, science reaches a point where the evidence is strong, yet the explanation remains uncertain. Dark matter is one of those moments. Astronomers can measure its influence with remarkable precision. They can calculate how much dark matter surrounds a galaxy. They can map dark matter halos using gravitational lensing. They can simulate the formation of cosmic structures using dark matter as the central ingredient. And yet, when physicists try to detect dark matter particles directly, the results remain silent. Detector after detector has searched for the faint signals that dark matter might produce. So far, none has delivered a clear answer. This silence does not mean the search has failed. In many ways, it has refined our understanding. Each unsuccessful experiment helps eliminate certain possibilities. Certain particle masses become less likely. Certain interaction strengths become more constrained. The range of possibilities grows narrower, but the mystery remains. Some physicists believe the solution may lie just beyond the sensitivity of current experiments. Perhaps dark matter particles interact with ordinary matter even more weakly than expected. If so, detecting them may require instruments that are far more sensitive than anything built so far. Future detectors may need to be larger, more shielded, more precise. Others believe the answer may lie in entirely different directions. Instead of searching only for particles that collide with atoms, scientists might look for more subtle signals. For example, dark matter might influence the behavior of stars within galaxies in ways that reveal new properties. It might leave faint imprints in the distribution of galaxies across cosmic time, or it might produce tiny distortions in the cosmic microwave background. In this way, astronomy and particle physics continue working together. Astronomy observes the universe on the largest scales. Particle physics explores the smallest scales. Dark matter sits exactly between these two worlds. It shapes the structure of galaxies, yet its nature likely depends on the physics of fundamental particles. Because of this connection, solving the mystery of dark matter could reshape both fields at once. If dark matter particles are discovered, they would represent the first known particles outside the standard model of particle physics. That discovery would open the door to entirely new areas of physics. New particles, new forces, perhaps even new dimensions of reality. But even if dark matter turns out to be something completely unexpected, the search itself continues expanding our knowledge. Each experiment improves our ability to detect faint signals. Each telescope extends our view deeper into the universe. Each simulation reveals new possibilities for how cosmic structures might form. Science rarely moves in straight lines. Often the path to discovery includes many wrong turns and unexpected results. Yet those detours are part of the process. They refine our understanding. They guide us toward better questions. They push us closer to the truth. The search for dark matter has already transformed cosmology. A century ago, astronomers believed the visible universe contained nearly all of the matter that existed. Stars, gas, dust, and galaxies were thought to account for everything. Today we know that ordinary matter represents only a small fraction of the universe, roughly 5%. The rest is something else. About 27% appears to be dark matter, and the remaining 68% consists of an even more mysterious component known as dark energy, which drives the expansion of the universe. In other words, the familiar matter that forms planets, oceans, living creatures, and stars is only a tiny piece of the cosmic story. Most of the universe belongs to things we cannot yet see or fully understand. This realization may feel unsettling at first, but it is also deeply inspiring. It reminds us that the universe still holds many secrets, that discovery is far from finished, and that the next breakthrough could appear at any moment. Perhaps a detector deep underground will capture the first unmistakable signal of a dark matter particle. Perhaps a telescope will reveal subtle patterns that point toward an entirely new explanation. Or perhaps a young scientist will look at the existing evidence in a new way and recognize something that everyone else has overlooked. However the answer eventually arrives, it will reshape our understanding of reality. It will reveal what most of the matter in the universe is actually made of, and it will illuminate the hidden framework that has guided the evolution of the cosmos for billions of years. Until then, the mystery remains. A quiet reminder that even in an age of powerful telescopes and advanced technology, the universe still has the ability to surprise us. When we think about the universe, it is easy to imagine that science has already uncovered most of its secrets. After all, we have spacecraft traveling through the solar system, telescopes capable of observing galaxies billions of light years away, computers that simulate the birth and evolution of cosmic structures. From a distance, it can seem as though humanity has mapped nearly everything there is to know. But dark matter reminds us that this impression is only an illusion, because when we look carefully at the cosmos, we discover that the majority of its contents remain unknown. Everything we see, every star, every planet, every glowing galaxy, belongs to a small minority of the universe's total mass. The visible universe is only the surface. Beneath that surface lies something much larger and far more mysterious. Dark matter fills the halos of galaxies. It stretches along the filaments of the cosmic web. It binds clusters of galaxies together across unimaginable distances. And yet it passes silently through the stars and planets without leaving a visible trace. In some ways, this situation resembles standing in a vast forest at night. You can see the trees illuminated by moonlight. You can hear the wind moving through the branches. But you know that most of the forest lies hidden in darkness beyond the reach of your vision. You can sense its presence. You can observe its effects. But you cannot yet see its full shape. Dark matter is that unseen forest surrounding the visible universe. A hidden structure whose presence is revealed only through gravity. And gravity, while powerful, tells us only part of the story. It reveals how much mass exists. It reveals how that mass moves. But it does not tell us what the mass is made of. That question remains unanswered. Perhaps dark matter consists of new particles waiting to be discovered. Perhaps it belongs to a hidden sector of physics that interacts only weakly with our familiar world. Or perhaps it will lead us toward a deeper theory of gravity that we have not yet imagined. Each possibility carries profound implications. Because solving the mystery of dark matter would not only explain the structure of the universe, it would also reveal new aspects of the fundamental laws of nature. Throughout history, moments like this have often preceded major scientific revolutions. In the 19th century, the strange behavior of light eventually led to the discovery of electromagnetism. In the early 20th century, unexpected observations of atomic structure led to the birth of quantum mechanics. Each time, a puzzling observation forced scientists to rethink their assumptions about how the universe works. Dark matter may represent the next such moment, a quiet anomaly that hints at deeper layers of reality waiting to be uncovered. Yet even as we search for answers, there is something peaceful about the mystery itself. The universe does not reveal all of its secrets at once. Instead, it invites curiosity. It encourages patience. It rewards those who continue asking questions long after the first clues appear. Astronomers will continue mapping the cosmic web. Physicists will continue building detectors sensitive enough to capture the faintest interactions. New telescopes will peer deeper into space and further back in time. And somewhere along this long path of discovery, the invisible matter shaping the cosmos may finally reveal its identity. Until then, the night sky remains a place of quiet wonder. The stars appear bright and familiar, but behind their gentle glow lies an unseen structure stretching across the universe. A structure built from matter that does not shine, matter that does not emit light, matter that quietly shapes the motion of galaxies and the architecture of the cosmos. And perhaps the most extraordinary realization of all is this: the visible universe, the stars we see when we look upward, is only a small part of the story. The true framework of reality lies mostly in darkness, a hidden skeleton holding galaxies together, guiding the formation of cosmic structures, and shaping the evolution of the universe itself. For now, that skeleton remains invisible, but its presence surrounds us, extending through every galaxy, every cluster, and every filament of the cosmic web. And somewhere within that vast invisible framework, the answer to one of the universe's deepest mysteries is waiting to be found. The hidden skeleton of reality. When we look up at the night sky, the universe feels full. Stars scatter across the darkness. Planets orbit distant suns. Entire galaxies glow softly through telescopes. It is easy to imagine that what we see represents most of what exists. But modern cosmology has revealed a much stranger truth. Almost everything we see is only a small fraction of the universe. The stars, the glowing gas, the galaxies themselves, these familiar things make up only a thin layer of cosmic reality. Beneath that visible layer lies something far larger, something invisible, something that quietly shapes the structure of the entire cosmos. Dark matter. If the universe were a vast building, dark matter would be its framework. The beams hidden behind the walls. The structural skeleton holding everything in place. Without that skeleton, the visible parts of the universe would not look the way they do. Galaxies would spin apart. Clusters would dissolve. The delicate filaments of the cosmic web would never have formed. Yet for all its importance, dark matter does not reveal itself easily. It does not glow. It does not absorb light. It does not interact with atoms in the ways we are used to observing. Instead, it moves silently through the universe, interacting almost entirely through gravity. And gravity alone has allowed scientists to trace its presence across cosmic history. The story begins shortly after the birth of the universe. In the early moments following the Big Bang, the universe was hot, dense, and nearly uniform. Tiny fluctuations in density existed, but they were extremely small. Over time, gravity began amplifying those tiny differences. Regions that were slightly denser pulled in more matter. As they grew heavier, their gravitational pull increased. This slow process gradually transformed the smooth early universe into a landscape filled with structure. Dark matter played a crucial role during this transformation. Because it does not interact with radiation, dark matter was free to collapse into gravitational structures earlier than ordinary matter. While normal matter remained tightly coupled to radiation during the first few 100,000 years of cosmic history, dark matter was already responding to gravity. Small clumps of dark matter began forming long before the first atoms appeared. These early clumps grew larger over time. They merged. They stretched into filaments. They formed halos large enough to attract gas and ordinary matter. When the universe cooled enough for atoms to form, ordinary matter began falling into these invisible dark matter halos. Gas accumulated. Clouds collapsed. The first stars ignited. In this way, dark matter acted as a kind of cosmic blueprint. It determined where galaxies would form. It shaped the large-scale architecture of the universe. The galaxies we see today grew inside the gravitational wells created by dark matter. Even our own galaxy is surrounded by a vast dark matter halo. This halo extends far beyond the visible stars of the Milky Way. If we could somehow see the halo, it would appear enormous, many times larger than the bright disk of stars we observe in the night sky. The stars themselves occupy only the inner region of this much larger structure. And the Milky Way is not unique. Every large galaxy appears to be embedded within a dark matter halo. These halos influence how galaxies rotate, how they interact with neighboring galaxies, and how they grow over time. When galaxies collide and merge, their dark matter halos merge as well. Over billions of years, these mergers help build the large galaxies we observe today. The universe we see is therefore deeply connected to something we cannot see. A hidden structure that formed long before the first stars existed. A structure that continues shaping the motion of galaxies even now. Without dark matter, the cosmos would look profoundly different. Galaxies would likely be smaller and less stable. Large clusters of galaxies might never have formed. The cosmic web itself might never have emerged. Instead of a universe rich with galaxies, stars, and planets, the cosmos might have remained a far smoother and emptier place. Dark matter gave gravity something extra to work with. It amplified the small fluctuations present in the early universe. It allowed structure to form faster and on larger scales. And in doing so, it helped create the conditions necessary for galaxies and eventually life to appear. This realization carries a quiet sense of wonder, because it means that much of the universe's history was shaped by something invisible, something that surrounded the earliest galaxies long before our own solar system existed, something that still surrounds our galaxy today. Even now, dark matter is passing through the Earth, through the atmosphere, through the ground beneath our feet. It moves silently through every object, every planet, every star. Trillions of dark matter particles may be flowing through your body every second, and yet we feel nothing, see nothing, notice nothing at all, because dark matter interacts so weakly with ordinary matter that it passes through almost everything as though it were not there. It is one of the strangest discoveries in modern science. An invisible substance filling the universe. A substance that outweighs all the stars and galaxies combined, and yet remains almost completely hidden from direct observation. The idea that most of the universe is invisible can feel almost unsettling at first. For centuries, human understanding of the cosmos was shaped by what could be seen. The stars, the planets, the glowing clouds of nebulae scattered across the Milky Way. Even when telescopes revealed distant galaxies, those galaxies still appeared as visible objects made of familiar matter. But dark matter changed that picture entirely. It revealed that the universe is not built primarily from the glowing material we observe. Instead, the visible universe floats within something much larger and far more mysterious. To understand this, imagine a city at night. From a distance, you might see only the lights, the illuminated windows, the glowing street lamps, the moving headlights of cars. Those lights give you a sense of the city's shape. They show where activity exists. But they do not reveal the full structure of the city. The roads, the buildings, the bridges, the power lines, most of that structure remains hidden in darkness. In many ways, the visible universe is like those city lights. Stars and galaxies mark the places where ordinary matter has gathered and begun to shine. But the larger framework holding everything together lies mostly unseen. Dark matter forms the deep infrastructure of the cosmos. It creates the gravitational wells in which galaxies form. It binds clusters of galaxies together across millions of light years. It stretches along filaments that connect distant regions of space. These filaments form the threads of the cosmic web. Along these threads, matter flows slowly under the influence of gravity. Gas streams along the filaments. Galaxies drift toward denser regions. Clusters grow larger as they gather surrounding material. All of this motion unfolds across enormous timescales. Millions, billions, trillions of years. From our perspective, the universe often appears calm and unchanging. But in reality, it is slowly evolving within the gravitational framework created by dark matter. Even the future of the universe is tied to this hidden structure. Over the coming billions of years, galaxies will continue merging. Clusters will grow larger. The cosmic web will gradually change shape as matter flows through its filaments. Eventually, distant galaxies will drift beyond the horizon created by cosmic expansion. From within any given galaxy cluster, the rest of the universe will slowly fade from view. But the dark matter halos surrounding those galaxies will remain. They will continue binding galaxies together long after the wider universe becomes difficult to observe. In this sense, dark matter not only shaped the past of the cosmos, it will also influence its distant future. And yet, despite its enormous influence, dark matter remains one of the least understood components of reality. The particles responsible for it have not yet been identified. The forces governing its behavior remain uncertain. Its true nature is still hidden. This mystery gives dark matter a unique place in science. It is both well established and deeply unknown at the same time. Astronomers can measure its gravitational effects with great accuracy. But the substance itself remains invisible. Like the wind shaping the surface of the ocean, dark matter reveals itself through motion rather than appearance. It moves galaxies. It bends light. It builds the scaffolding of cosmic structure. But it does not shine. For scientists, this mystery is not frustrating so much as inspiring. Because every unanswered question represents an opportunity for discovery. Somewhere within the physics of dark matter lies new knowledge about the universe. Perhaps new particles. Perhaps new forces. Perhaps entirely new ways of understanding the laws of nature. Throughout history, many of the greatest scientific breakthroughs began with observations that did not quite fit existing theories. Small anomalies, unexpected measurements, puzzles that refused to disappear. Dark matter may represent one of the largest puzzles ever encountered. A puzzle spanning the entire universe. And solving it will require patience, new experiments, new ideas, and perhaps new ways of looking at reality itself. Until then, the universe continues its quiet evolution. Galaxies drift along the filaments of the cosmic web. Stars are born and fade. Clusters gather slowly under the pull of gravity. And behind it all lies the invisible framework of dark matter, the hidden skeleton of the cosmos. Silent, unseen, yet responsible for shaping nearly everything we observe in the night sky. There is something quietly profound about realizing that the universe is mostly invisible. For thousands of years, humanity looked up at the night sky and believed that what we saw was the universe itself. The bright stars, the wandering planets, the faint glow of the Milky Way stretching across the darkness. Even after telescopes revealed distant galaxies and immense cosmic distances, the basic assumption remained the same. The visible universe was the universe. But modern astronomy has revealed a very different picture. What we see is only the surface, the luminous layer. Beneath it lies something much larger, something hidden that quietly shapes the structure of everything around us. Dark matter does not shine, yet it surrounds every galaxy. It stretches across the filaments of the cosmic web. It forms halos that extend far beyond the visible edges of galaxies. And because of its gravity, the universe developed structure in the way we see today. Galaxies did not form randomly. They grew inside dark matter halos. Clusters of galaxies gathered at the intersections of dark matter filaments. The enormous cosmic web that spans billions of light years emerged from the slow collapse of invisible matter. In other words, the universe we observe today was built on a foundation we cannot see. The stars are like lights decorating a structure that already existed. They illuminate the skeleton, but they are not the skeleton itself. Without dark matter, the cosmos would likely have evolved in a very different way. The early universe would have remained smoother for much longer. Gas would have struggled to collapse into galaxies. Large cosmic structures might have formed far more slowly, if they formed at all. The existence of dark matter accelerated the growth of structure. It amplified the tiny fluctuations left over from the earliest moments of cosmic history. Those small ripples grew into galaxies, clusters, and the enormous web-like structures astronomers observe today. In this way, dark matter played a crucial role in shaping the environment where stars and planets eventually formed. And within those planets, life eventually appeared. This realization adds a quiet layer of wonder to the story of the cosmos. Because the existence of galaxies, stars, and even the conditions that allowed life to emerge may depend in part on something we cannot yet see or fully understand. Dark matter helped build the stage on which the visible universe performs. And yet, its true nature remains hidden. Somewhere within the laws of physics lies the explanation. Perhaps it will come from a new particle discovered in a detector deep underground. Perhaps from unexpected data gathered by a telescope mapping distant galaxies. Or perhaps from a theoretical breakthrough that reveals new layers of reality beneath the familiar world of atoms and forces. However the answer eventually arrives, it will likely reshape our understanding of the universe. Just as previous discoveries transformed our view of the cosmos. The realization that Earth orbits the Sun. The discovery that galaxies exist beyond the Milky Way. The understanding that the universe itself is expanding. Each of these ideas once seemed radical. Each required humanity to rethink its place in the cosmos. The discovery of dark matter may represent another step in that long process. A reminder that reality is often more complex than it first appears. Even now, as you imagine the quiet vastness of space, dark matter surrounds every galaxy. It fills the halos of galaxy clusters. It stretches along invisible filaments connecting distant regions of the universe. And it continues shaping cosmic evolution in ways we are only beginning to understand. The stars we see are only the brightest markers of a much larger structure. A structure that has guided the growth of the universe for nearly 14 billion years. And perhaps the most extraordinary part of this story is that the mystery remains open. The universe has revealed enough clues to show that dark matter exists. But it has not yet revealed the final answer. That answer waits somewhere within the hidden depths of reality, waiting for the moment when curiosity, observation, and imagination finally come together. Until then, the night sky remains a place of quiet reflection. The stars shine gently against the darkness. Galaxies drift slowly through the cosmic web, and behind them all lies the invisible framework that holds everything together. The hidden skeleton of the universe.